Right. Good afternoon, everyone. We have been discussing adders. In that we have seen parallel adder. In that again we have seen parallel ripple carry adder. So there is a specific pessimism in our n delta formula. So to eliminate the pessimism, what we have done? To eliminate that pessimism, we have used the carry generation time separately, some generation time separately, if it is specified. We have seen how to calculate propagation delay of a n-bit ripple carry adder. That is n minus 1 Tc plus maximum of Ts comma Tc. N minus 1 Tc plus maximum of Ts comma Tc. Right? Now, let us see some more questions which we need to focus for competitive exams. I hope everything is clear till this n-bit adder. So in this we have used the n minus 1 Tc plus maximum of Ts comma Tc, and we have solved some of the questions also. And I might have cleared why we need to consider the minimum time is 100 nanoseconds. Why can't we take lesser than that? If you take greater than 100 nanoseconds for one 4-bit addition, what happens also we have discussed. I think no doubts in that. Am I audible? Am I audible? Yes. Thank you. Thank you. Okay. Fine. Now, a full adder is taking 2 nanoseconds to produce carry and 4 nanoseconds to produce sum. And inputs A3, A2, A1, A0 is equals to 1101 and B3, B2, B1, B0 is equals to 1111 and input carry C0 is equals to 0. What is the propagation delay to stabilize all the outputs. Question to be understood correctly. A 4-bit what is a propagation delay to stabilize all the outputs in a 4-bit ripple carry adder. Question, ripple carry adder. Calculator, the propagation delay. Harsha, I will discuss. Ajay, try to go through that clearly, you will understand. Otherwise, in question hour, I'll help you. So 1 1 0 1 1 1 1 1 and also 1. If you have any doubt, assume all the inputs and outputs were initially 0. All the inputs and outputs were initially 0. If it is not mentioned anything also, we go with the same. And here, if it is mentioned also, we consider that. See, what we are applying here, it is a 1, 1, 1, then 0, 1, and here 1, 1, and here it is 1, 1. All were zeros and all the outputs were zeros. For example, here it was 0, it was 0, it was 0, it was 0. I'm not saying that it will be 0. And it was 0, and it was also 0, it was also 0, it was also 0. Initially, all these were there. At t equal to 0, for example, at t equal to 0, all these are applied. All these inputs are applied. Then what can be the time required to stabilize all the outputs? Oh, input carry is 0. Sorry. Input carry is 0. Yes, it is 0. It is also 0. Sorry. Yes, input carry is 0. In a full adder, carry time is 2 nanoseconds, sum time is 4 nanoseconds. What is the time required to stabilize all the outputs? Can you guess what can be the outputs here? 0, 1 carry, 0, 1 carry, it is 1, and it is 1, here it is 1, and final carry is 1. This is a result. If you're adding these, 0 plus 1 plus 1 is 2, which is 1, 0, 1 is 0, 1 is the sum, 0 is sum, sorry, 1 is carry, 0 is sum. Now 1 plus 0 plus 1, again 2, 1 is carry, 0 is sum, 1 plus 1 plus 1 is 3, 1 is carry, 1 is sum, 1 plus 1 plus 1, again 1 is carry, 1 is sum. Right, now, so what we are observing here, is this changing? No, it is not changing. How much time it takes, sir? At what time this 0 will be available? 0 nanoseconds. Why? It is not changing. Before applying inputs, it was 0. After applying inputs, also it is 0 only. So is it changing? No. If it is not changing, I don't need to consider propagation delay. How much time it takes? 0 nanoseconds. So is it changing? Is it changing? Yes, it is changing to 1. It is changing to 1. So how much time it takes? From the point input supplied to change carry to 1, it is taking how much time? 2 nanoseconds. Anyone has any doubt? 2 nanoseconds. Is there any doubt in that? Yes, it is getting ready in 2 nanoseconds. It is changing from 0 to 1 in 2 nanoseconds because this full adder is getting 110 at 0 time. Yes, carry is changing to 1. Carry is changing to 1 in how much time? Carry time is how much? 2 nanoseconds. Now, here 0, 1, what will be here? 0. If you are getting 0, 1, 1, then it is changing to 1. It is changing to 1. Yes. See, with 1, 0, 0, it was what? Not changing. Carry is not changing. After getting this one, because of 1, 1, 0, yes, this is changing to 1. This is changing to 1. Am I right? Yes. After getting this carry only, because of 1, 1, 0, this carry is becoming 1. This will take how much time? After getting this one, only it is changing to 1. That means after getting this one 2 nanoseconds, again carry time is 2 nanoseconds, is 4 nanoseconds. 4 nanoseconds. Now, here, understand correctly. Here, this is changing to 1. Any doubt in that? It was 0. It is changing to 1. From where it started changing to 1? Can you say what is the time required to change to 1? Or when it is changing to 1, how much time it takes? At this case, to change from 0 to 1, how much time it takes? Please help me. How much time it takes to change that carry? Everyone should answer. Yes, 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 yes. Right. Most of you are doing a mistake. Listen, listen. Very good. Akash. Right. See, here it has to change to 1. So, is it waiting for this 1? No. With 110 at 0 time. Be clear about this. With 110 at 0 time, it is changing to 1. So required inputs to change to 1 is not required 111. Be clear about this. It is not required to get 111. This one we are getting at 4 nanoseconds, but this one is not required to change this carry to 1, because with 110 also it is becoming 1. So it started, carry started changing to 1 at what time? T equal to 0 itself, because with 110 itself it is carry 1. Check it correctly. With 110 carry is 1, with 111 also carry is 1. But where it started changing, with 110 itself carry is becoming 1. So at what time this will be ready? 2 nanoseconds. Be clear about this. 2 nanoseconds. This carry 1 is available in 2 nanoseconds from the point input supplied. It is not waiting for this carry. Because with 110 which are available at 0 time, it started changing to 1. So this carry becomes 1 in 2 nanoseconds. Yes. Yes. Coming to this sum. Coming to this sum. What is it here? This sum, with 110 it was 0. With 000 it was 0. Because of this one only, this is changing to 1. Be clear about this, sir. It is changing to 1 because of this one only. That means it has to wait getting this one, then it is changing to 1. So after getting this carry 1, it started changing sum to 1. So it takes 4 more nanoseconds. Means 4 nanoseconds to get carry here. Then onwards, sum started changing to 1. So it is again 4 nanoseconds. Means it is ready in 8 nanoseconds. This is changing from 0 to 1. So it is ready in how much time? 8 nanoseconds. Why? It needs this 1, then only it can change it to 1. That means because of this one only, sum is changing. But to get carry 1 here, it is not required 1 here. With 110 itself, it is changing from 0 to 1. That means to get 1 here, it takes 2 nanoseconds only. But here to get changes in the sum, it is expected to get 1, then only with 111 we are getting 1 is the sum. So to get 1 here, it takes 4 nanoseconds. So after getting this change, there is a possibility for changing sum, that is to 1. So it takes 4 nanoseconds to get to 111. To get 111, it takes 4 nanoseconds. Then onwards, it takes 4 nanoseconds, because it is 8 nanoseconds. Right? See here. What is the time required to get 1 here? Observe this. It is changing to 1. It is changing to 1. In how much time? This will be ready in how much time? This will be ready in how much time? 2 nanoseconds. Why? With 110 itself, it is changing from 0 to 1. That means it is ready in 2 nanoseconds. It is ready in 2 nanoseconds. And once again, here also it is changing to 1. Here also it is changing to 1. This also changing to 1. In how much time? After getting 111. At what time we are getting 111? This 11 is available at 0 time. This one is ready in 2 nanoseconds. Means so this 111 is ready in 2 nanoseconds. Then sometime is how much? 4 nanoseconds. This will be ready in 6 nanoseconds. This one is ready in 6 nanoseconds. And what about this? It was 0. After that also it is 0 only. How much time? 0 time. It is not changing. It is not changing. Each and every output, if you are analyzing correctly, all the outputs will be ready in how much time? 8 nanoseconds. A simple principle I am using. If there is a change in the output due to changes in the input, add delay from the point input stabilized. If there is a change in the output due to changes in the input, right? With the available inputs at 0 also, if it is changing, then we don't need to wait for other inputs. See, here 110 at 0 time it is available. With 110 itself, carry becomes 1. That means from 0 time it is you have 110. At 0 time it is started changing to 1. Means it is ready in 2 nanoseconds only, because it is not waiting for this one. It is not waiting for this one. If it is getting 1 here, then it is changing sum. So Sum is waiting for getting 111, but with 110 itself, carry is changing to 1. That means this 110 is available at 0 time. After getting 111 also, carry is 1 only. After getting 111 also, carry is only. With 110 also, with 110 also, with 110 also, it is a carry 1. It is carry 1. Understanding? With 110 also, carry is 1. That means that 1 is available in 2 nanoseconds. Right? So finally, each and every output, if you are observing, it is taking total 8 nanoseconds. Don't go with carry, changing, carry, changing, carry, changing. Just a minute. Right. If anyone is having any doubt, please mention in the chat box. Please mention in the chat box. Yes. I will explain Triveni once again. This type of questions we have been getting frequently in GATE exam. Yes, I will do. For everyone, I will do once again. I will explain once again. The only thing I suggest you is, yes, I will do. No. Here, propagation delay for a particular input. When inputs are not specified, then we go with the worst case propagation delay, assuming that each and every dependency is there. Assuming each and every dependency is there, we are calculating propagation delay. That is the worst case propagation delay when particular inputs are not applied. Akash, I will explain everything. Please wait. When you are considering, right, general propagation delay, right? So if you are observing here, each and every output time is specified. When I asked what is the delay of this entire circuit, means whichever is maximum in all these should be considered. Which one is maximum in all these? 8 nanoseconds. That's what I'm saying, that propagation, maximum of all. Manisha. Right? Yes. In all these, whichever is maximum, we are considering. Right. Huh. I will explain once again. Be clear about this, sir. Most of you may be new to this type of analysis, but questions are based on this only. There must be some difference after these classes and before these classes. When you are comparing yourself, you must be changing your way of thinking on digital circuits, because the questions we have been getting like that. Please understand each and every word I am mentioning here. What we are applying, first let me write that. what we are applying here, C naught is 0, and here we are applying, let me take that 1 1 0 1 1 1 1 1 1 1 0 1 1 1 1 1. Then what were the outputs? Initially, before applying these inputs, assume at t equal to 0, we are applying, at t equal to 0, we are applying all these. Understand correctly? At t equal to 0, we are applying all these. Correct? At t equal to 0, we are applying all these. And before applying these inputs, what was the inputs? All zeros means these were all zeros. These were all zeros. All these were zeros. Understand correctly? Now what should I do? Wherever there is a change in the output, there we need to consider propagation delay. From the point inputs changed. Right? See, what I defined the definition about propagation delay, if there is a change in the output due to changes in the input, the change is occurring in output after propagation delay from the point inputs change. If there is a change in the output due to changes in the input, the change is occurring in output after propagation delay time from the point inputs changed. Am I right? If there is a change in output due to changes in input, change is occurring in output after propagation delay time from the point inputs changed. So where should I consider propagation delay? If there is a change in the output due to changes in the input, there only we need to consider propagation delay. So all these were zeros. Yes, because of these inputs, is there any change in these outputs? Yes, here it is changing to 1. Any doubt in that? Yes, it was 0. It was 0. Let me show you that. It was 0. It is changing from 0 to 1. It is changing from 0 to 1. Correct? How much time it takes from the point inputs applied? Carry is changing in carry time. What is the carry time? 2 nanoseconds. If anyone is having any question, let me know. Tell this point. See, here it is changing. Is there any change here? No change here. Then what time it is this 0 is available? 0 time only, because it is not changing because of these. Before applying these inputs, it is 0 only. After applying these inputs also, it is 0 only. Is it changing? Not changing. It is not changing. That means it is a 0 time. So if there is a change, consider propagation delay. If there is no change, no need to consider propagation delay. Right? Now, with 0 1 1, now see, with 0 1 it was 0 only, but with 0 1 1 we are getting 1 here. Am I right? With 0 1 1, with 0 1 1 it is changing to 1. Any doubt in that? So to get change here, it has to wait for this 1, because with 0 1 1 only we are getting 1 here. With 0 1 0 it is not 1. At t equal to 0, 0 1 0 is there. With 0 1 0 we are not getting 1 here. So after getting 1 here, then with 0 1 1, yes, carry is becoming 1. Am I right? That means it has to wait to get 1 here. After changes have occurred here, change is occurring here. That means it has to wait to stabilize 1 here. That means it is taking 2 nanoseconds. Time required to stabilize the inputs is 2 nanoseconds. Time required to stabilize the output, it takes 2 more nanoseconds, because carry is changing. So here we are getting 1 after 2 more nanoseconds from the point this carry is stabilized. That means this 1 will be ready at what time? 4 nanoseconds. Check it correctly. 4 nanoseconds. Am I right? Am I right? What about this? It is not changing, because before applying these inputs it is 0 only. After applying inputs also it is 0 only. So is it changing? Not changing. Then propagation delay is 0. If it is not changing, no need to consider propagation delay. Correct? Yes. With 1 1 0, with 1 1 0, what will be here? Carry is 1. So this one is not available at 0 time. This one is available at 4 nanoseconds. But at 0 time, what is the inputs we have? 1 1 0. with 110 itself, carry is becoming 1. That means this 1 is available at what time? 2 nanoseconds. If anyone is having any questions, let me know. So to get 1 here, it is not required 111. To get 1 here, it is taking 4 nanoseconds. But with existing 110 itself, it is changing to 1. In how much time? 2 nanoseconds. Because this 110 is available at 0 time itself. With 110 itself, carry is becoming 1. That means it takes 2 nanoseconds. So to stabilize carry 1 here, it is taking 2 nanoseconds only. Because with 110 itself, carry is becoming 1. But here it is changing to 1. Here sum is changing to 1. But to get changes here 1, we need to have 1, 1, 1. Am I right? We need to have 1, 1, 1. Then only we get here 1. It is changing to 1. It is changing to 1. But for getting changes here, we need to get 1, 1, 1. To get 1, 1, 1 itself, it is taking 4 nanoseconds. Then onwards, sum is changing. Sum change time is 4 nanoseconds after getting inputs. So to get 1, 1, 1 inputs, it is 4 nanoseconds. After that, it takes 4 more nanoseconds to change the sum. That means here it is becoming 1 in how much time? 4 nanoseconds to stabilize the input. Because of this 111, sum is becoming 1. So 111 is changing to 1 after 4 nanoseconds. Yes, 111 is available at 4 nanoseconds. It takes 4 more nanoseconds, means it is available at 8 nanoseconds. Right? Now, here, with the 110, which are available at 0 time, this is changing to 1. Check it correctly. With available inputs 110 at 0 time, it is changing to 1. It is changing to 1. How much time it takes? The required inputs 110 available at 0 time, it takes 2 nanoseconds to change to 1. Now, here this is changing to 1. This is changing to 1 because of 111. To get 111, how much time it takes? This 11 is available at 0 time. This 1 is available at 2 nanoseconds. So to get 111, it is taking 2 nanoseconds. Then onwards, the sum is changing to 1 in 4 more nanoseconds, means this will be available at 6 nanoseconds. Right? So each and every output stabilization time we have calculated. To stabilize all the outputs, how much time it is taking? Whichever is largest in all these is 8 nanoseconds. So don't analyze delta for this, delta for this, delta for this. That is not the correct way. So dependency of previous bit addition is required to be analyzed. So is it waiting for carry from previous bit addition or not? If it is waiting, then you need to wait for that much time. If it is not waiting for carry from previous bit addition, then start analyzing from 0 time itself. Yes, most of you are asking for one more explanation. Please let me know. Harsha, what is it here? If A1 input is 1, that means you are saying here it is 1, 1, then it is 2 nanoseconds only. If you are having here also 1, 1, it is taking 2. I'll take one more example. I will take one more example. You will get more clarity. Try to understand this, sir. Right? If there is a change in the output due to changes in the input. Shilpa, we need to use formula when general propagation delay is asked. When particular input changes are applied, then I should know where there is a change in the output, there only we need to consider propagation delay. Right? Whenever it is asked what is the propagation delay of a circuit, I don't know what is the inputs applied, then I go with maximum or worst case propagation delay. Yes, 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 yes. So when you're analyzing one full adder, we should go with maximum of TS and TC. When you are using n-bit adder, this is the way we need to analyze. Right. Don't get saturated. I'm there to help you. If you're not understanding, I will wait in the question hour, whatever the time it is required. Yesterday, I didn't know what was the problem. Suddenly it got off. I think there may be problem with the portal. Once again, I tried to log in, but as it is timed out, it is scheduled till 6 only. That is the reason. Once time is out, I cannot re-log in. If it is continued, we can continue for time required. But once it is logged out or once it is out, then it is not possible to log in after scheduled time. It is 2 p.m. to 6 p.m. It is scheduled. But beyond that, if you are trying to log in, it is not possible. Within the time, if it is any problem, we can rejoin the meeting. That's a problem yesterday. So, Surya Teja, which one you are asking, I don't know. But I will answer with respect to each and every one's doubt later. Please wait and understand what I've been conveying. For everyone, right? I will discuss every question of you clearly. Please wait. Understand concept correctly. When input changes are provided, what will be the propagation delay? What will be the propagation delay? I think 2019 GATE EC paper, there was a similar question. But that is very different. I'll show you that later. Already given. I'm not framing now. I'm not expecting this type of questions. Already given. Don't take it easy. Try to understand correctly. If there is a change in the output, yeah, I will take Ashutosh. I'll take some more examples. Please wait. If there is a change in output due to changes in the input, then add propagation delay. Observe correctly what I've been saying. If there is a change in the output due to changes in the input, then change is occurring in output after propagation delay. But what we need to observe here is, yes, inputs are changing. Because of that, is there any change in the output? So, is it required to wait for changes in the inputs? Or some inputs are stable, other input is changing. If because of this other input changes, if there are changes in the output, we need to wait for this other input. Example already we have discussed. What is it here? OR gate is there. A is 0 to 1, B is changing from 0 to 1. A is already 1, B is changing from 0 to 1. I clearly mentioned that. Right? If you observed a simple OR gate, which we have discussed. From day one, I start building the basics. If you are understanding those, you won't get doubts here. The problem here is you are remembering how it is drawn. No, you need to apply the concept. See, why? 0, 0, it was 0. Yes, 0 to 1. Because of this change in A, it is changing to 1 after propagation delay time. Here, we need to consider propagation delay. Because it is changing, because output is changing because of this change in the input. Right. Now again, here, the input is changing. Is it changing the output? No. That is the reason we haven't considered propagation delay. Have you considered propagation delay here? No. With the existing at this time itself, it is becoming 1. With the existing at, for example, let me say that t equal to 0 at 2 nanoseconds, at 4 nanoseconds, at 6 nanoseconds, at it is 8 nanoseconds if I say, with respect to time slot. So at 2 nanosecond it is applied 1, because that itself output is 1. At 4 nanosecond again it is changing. Because of this change, output is not changing. So do I say that output is becoming 1 after 6 nanoseconds? No. If I say this is delta, Do I say that 4 nanosecond plus delta it is becoming 1? No, already it is 1. So here input is changing, output is not changing. There we don't need to consider propagation delay. Yes, again here A is changing from 1 to 0. Because of that output is 1 only. Because for 1 1 OR gate output is 1, for 0 1 OR gate output is 1. So is there any change in the output? No change. Then we don't need to consider propagation delay. And here A is 0, B is 0. Because of this, output is changing. Output is changing, so I need to consider propagation delay. I need to consider propagation delay. Right? If there is a change in the output due to changes in the input, change is occurring after propagation delay time from the point inputs changed. Definition should be understood correctly. If there is a change in the output due to changes in the input, change is occurring in output after propagation delay time from the point inputs changed. Right? If there is no change in the output due to changes in the input, even though input is changing, see here for this full adder 2, it is changing. Because of this change, is it changing? No. Then it doesn't need to wait for getting 1 here. With existing 110 itself, it is 1. At what time this 110 is available? At 0 time. At 0 time, the carry started changing to 1. So in how much time it will be ready? In 2 nanoseconds only. It is changing. Because of this change, is it changing? No. With the existing 110 itself, it is 1. Because of this change, there is a change in the sum. Then it has to wait for getting 1 here. So after getting 1 here, it is changing sum to 1. So the change in sum is occurring because of this carry change. So this full adder 2 has to wait for this carry 1 to change sum. To change carry doesn't need to wait, because with the existing 110 itself, it is changing to 1. With 111 also it is changing to 1. Do I need to wait for this 1 now? No. Because with 110 carry is 1, with 111 also carry 1. So here getting 1 is not because of this change. Then it is not waiting for this carry change to 1. But to get 1 here in the sum, it has to get 1 here. To get 1 here, it is taking 4 nanoseconds. No doubt in that. So we are getting 1 here at 4 nanoseconds. After getting 1, sum is changing to 1. So some time delay is how much? 4 nanoseconds. Time required to get 111 is how much? 4 nanoseconds. So 4 plus 4, it is becoming 8 nanoseconds. Right? Understanding? Right? So if there is a change in the output due to changes in the input, there only we need to consider propagation. So I'm not saying all the statements, everything is same. Carry time is 2 nanoseconds, sometimes is 4 nanoseconds. Carry time is 2 nanoseconds, sometimes is 4 nanoseconds. Now, inputs I'm specifying, you need to calculate. A3, A2, A1, A0 is a and input carry C0 is 1. What will be the propagation delay to stabilize all the outputs? Two nanoseconds. Carry time is 2 nanoseconds, sometimes is 4 nanoseconds. That's what I mentioned. Carry time is 2 nanoseconds, sometime is 4 nanoseconds. What is the time required to stabilize all the outputs? Same thing, assuming all the inputs were zeros, all the outputs were zeros initially. Please try, don't take it easy. It is not a formula based analysis, sir, until unless you are understanding propagation delay correctly. We cannot answer these type of questions, sir. 2 times, sir, already given these type of questions, sir, in exam. What were initially? This is 0, this is 0, this is 0, this is 0, this is also 0, 0, 0, initially. Now, yes, it is applied these inputs. 1, 1, 1. Here it is changing to 1. In how much time? 2 nanoseconds. Here it is changing to 1. In how much time? 4 nanoseconds. Anyone has any questions? Right. Now, here it is changing to 1. In how much time? 2 nanoseconds only. Why? 110 is available at 0 time itself. With 110 itself, it is changing to 1. Yes, it is ready in 2 nanoseconds only. Right? Now, with 110 here again carry is changing to 1. In how much time? 2 nanoseconds only. With 110 itself, it is changing to 1. How much time? It is 2 nanoseconds only. Yes. After getting 1 here, the sum is becoming 1. That means how much time? 2 nanoseconds plus 4 nanoseconds. These are 6 nanoseconds. And again, here 110, it was 0. With 111, it is becoming 1. In how much time? After getting this 111, 4 nanoseconds means it is 6 nanoseconds. Yes, again, with 110, it is 0. With 111, it is becoming 1. In how much time? After getting 111, 4 nanoseconds means it's total 6 nanoseconds. All the outputs are ready in how much time? 6 nanoseconds. 6 nanoseconds. Ravindra Swami, very good. Yes. Akash. Right? Gopal Krishna, very good. Bharat. Many have answered correctly. Right? Sajjan Singh. Shivalila. Very good. Yes. Excellent. People have been analyzing in a right way. Yes. Very good, Pratyush. Super analysis. Very good. Right. Many of you are understanding right way about the propagation delay. Right? So, please solve this later. Please solve this later. TC is 2 nanosecond, TS is 4 nanoseconds. These are the inputs applied. Before applying inputs, all the inputs were zeros, all the outputs were zeros. Calculate propagation delay later, not now. Please understand correctly. What is it here? So we need to calculate propagation delay for this later, not now. Let me know your answer later, not now. Right. Once again, back to general propagation delay. People are raising hands, sir. I will discuss your doubts, sir, in question hour. Please wait. Yogesh, please wait. Go through the slides, sir. Try to understand, and then I will help you later. If I do what you are expecting now, everyone will do the same. Do you accept? If others are asking for the same, do you accept? Yogesh Kumar. Right. What else we have discussed here is in ripple carry adder. At 0 time, we have applied all the inputs. In worst case, if it is changing, it is taking TC time, and here it is TS time. And after getting the C1 changes, if you are getting changes here, then it is 2TC. Then if it is getting here, how much time here? TC plus TS. And again here, 2TC. After getting this C2 changes, if you are getting C3 changes, it is 3TC. At what time this S2 will be ready? 2TC plus TS in worst case or maximum. So when you are getting the changes in C out, it takes 4TC, and here it is 3TC plus TS. So finally what we have discussed, Tn bit is equals to n minus 1 TC plus maximum of TS comma TC. This is a worst case propagation delay. When we don't know what is the input changes. When we don't know what is the input changes, this is the propagation delay. If you are provided with inputs, then we should analyze for actual propagation delay. When input changes are provided, we need to calculate actual propagation delay. When input changes are not provided, then we go with the general propagation delay, which is a worst case propagation delay, assuming each and every dependency is there. Assuming that we are proceeding to calculate a propagation delay. So in this, what is this n minus 1 TC time? Carry rippling time. According to our discussion, what is it here? TC, TC, TC. There is a 3 TC time only for carry rippling. So each full adder is waiting for carry from previous bit addition. Observe correctly. Each full adder is waiting for carry from previous bit addition. This carry rippling time is wasted. Because each full adder is waiting for carry from previous bit addition. That is the reason each full adder is waiting for carry. That is the reason entire n minus 1 TC time, or in this 3 TC time in 4-bit adder. In 4-bit adder, 3 TC. N minus 1 TC means 3 TC time is wasted in waiting for carry only. As each full adder is waiting for carry from previous bit addition. Instead of this, if I am providing carries for each and every full adder, so this full adder 1 is not waiting for C1, I am providing C1. This full adder 2 is not waiting for carry, I am providing C2. If I am providing C3, then it doesn't need to wait for carry from previous bit addition. Point should be understood correctly. Concept I am going to address now. So if I am providing carries for each and every full adder, it doesn't need to wait for carry from previous bit addition. Then I can save n minus 1 TC time. As each full adder is waiting for carry from previous bit addition, as each full adder is waiting for carry from previous bit addition, it is wasting n minus 1 TC time. It is wasting n minus 1 TC time. Instead of this, what I'm saying that I will provide carries for each and every full adder. I will provide carries for each and every full adder. Then let us see what happens. So now the circuit, full adder 0, we have a carry at 0 times. But full adder 1 was not having. Full adder 1 was waiting for carry from previous bit addition. Now what we are saying that we are providing C1 also. Once again, one more full adder 2, A2, B2, and also C2 is provided. Full adder 3, and again A3, B3, and here it is C3. Then what happens here? It is not waiting for carry from previous bit addition. Then how much time it takes to complete the addition? How much time it takes to complete the addition? One full adder delay. It is one full adder delay. Try to understand this correctly. If you are providing carries for each and every full adder, then addition can be completed in one full adder delay. Correct? Because it is not waiting for carry from previous bit addition. Because we are providing carries C1, C2, C3. If you are providing carries C1, C2, C3, right? If you are providing carries for each and every full adder, then it doesn't need to wait for carry from previous bit addition. Then in one full adder delay, which is nothing but maximum of TS comma TC, addition will be completed. But who is providing this C1, C2, C3? You, me. I am providing C1, C2, C3 means already I have done addition. If I am providing C1, C2, C3 means without adding these numbers, how would I know these numbers C1, C2, C3? Yes, I don't know. If I add, then I will come to know C1, C2, C3. That means already I am doing addition. If already I have done the addition, why do I need this adder circuit? What for I want to use this adder circuit? To complete the addition. I don't want to involve. I may be doing a mistake, manual mistakes. The system will not do the mistakes. That is the reason I'm using this design or is that adder circuit. But what you are saying that by adding, I'm providing C1, C2, C3 means you are adding means already addition is completed. Why do we need this adder circuit? So you should not involve in that. That means the C1, C2, C3, you are not calculating and applying. For C1, C2, C3, I am using a separate circuit. Point should be understood correctly. To estimate the C1, C2, C3, I am using a separate circuit. I am not adding and applying that. If I am already adding, why should I use this adder circuit? Not required. I don't need this adder circuit. I hope you are following. So, if I am providing C1, C2, C3 means addition is already completed. If addition is completed, I don't need to use this adder circuit. right? Then what should I do? The C1, C2, C3, instead of from previous bit addition, I'm providing a separate circuit for C1, C2, C3. By using additional circuitry, we are estimating C1, C2, C3, utilizing available information at zero time. What is that zero time available information? A0 to A3, B0 to B3 and C0. This is available information at zero time. Utilizing this available information, estimating C1, C2, C3. Estimating C1, C2, C3. Correct? So, by using additional circuitry, we are estimating C1, C2, C3. If this additional circuitry is estimating carries before it is generated from previous bit addition, point should be understood correctly. I am not involving in providing C1, C2, C3. I am providing a circuit for estimating C1, C2, C3. To estimate C1, C2, C3, I am using additional circuitry. If this additional circuitry is taking lesser time than carry rippling time. If the additional circuitry we are using to estimate C1, C2, C3 is taking lesser time than carry rippling time, then we can save time. Then we can save time. What is our aim here? I want to save time. How can I save time? What was the waste? What was the problem in the previous one? As each full adder is waiting for carry from previous bit addition, there is a dependency. That is the reason carry rippling time is wasted. That is the reason instead of carry rippling, let us estimate carry for each and every full adder with the available information at zero time. Then, if the additional circuitry is used to estimate the carries, taking lesser time than carry rippling time, obviously it can save time. So, what is the duty of additional circuitry? Estimating carry before it is generated from previous bit addition. So, additional circuit, the duty of additional circuitry is estimating carries before it is generated from previous bit addition. Before it is generated from previous bit addition. That is the reason it is named as looking ahead about carry. Looking ahead about carry. So it is named as a carry look ahead adder. Carry look ahead adder. CLA. Carry look ahead adder. Looking ahead about carry before it is generated from previous bit addition. So by using additional circuitry, we are estimating C1, C2, C3. If the additional circuit delay is lesser than carry rippling time, there we can save time. So by using additional circuitry, we are looking about carry early, ahead. So it is named as a carry look ahead adder. Carry look ahead adder. So what is the additional circuitry required to estimate C1, C2, C3? Let us see. Right. Are you here? Are you there? Are you understanding my words? Right? Yes. Very good. Toy Jakshudu. Right. Guessing that. Yes. Very good. Yes. So by using additional circuitry, we are estimating carries for each and every full adder. The carry estimation we are doing before it is generated from previous bit addition. That is named as looking ahead about carry. So now let us see what is the additional circuitry required to estimate carries. Right? A, B, C, I. I'm writing once again, full adder. Once again, full adder. Because what can be the circuit required to estimate carries I'm doing now? Yes, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. Someone is raising hands, right? I will answer for your doubts later. 1, 0, 1, 1, 1, 0, 1, 1, 1. If there is any problem, like audio or video or something else, please mention in the chat box instead of raising hands. Please mention in the chat box I will look at the okay. Right. Now for each and every combination, let us see what is the output. What is it here? 0, 0, 0, 1, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 1. This is outputs for each and every combination. Each and every combination. Ashish, Shrikant Yadav, Abin Francis. Please down the hands. Please down the hands. Ashish Kumar, Shrikant Yadav. Shrikant Yadav. Right. Please carry your doubts. I will explain every doubt in detail. Right. Please wait. Right. So I will show you the slides. I will ask you to go through right slides and I will help you. Please wait until the question hour. Please. Right. Now, so I am writing truth table easily. Some of you may be doubting that how is writing this truth table that much easily. I have my own way to write a truth table. Simple thing is outputs is number of ones in the inputs. Outputs is number of ones in the inputs. May not be understanding, right? See, 0, 0, 0. How many ones are there? 0, 0, 0. 0, 0, 1. How many ones are there? 1, 0, 1. 0, 1, 0. How many ones are there? 0, 1. 0, 1, 1. How many ones are there? 2 ones is nothing but a 1, 0. 1, 0, 0. One input is 1, 0, 1. 1, 0, 1. 2 ones, 1, 0. 1, 1, 0. 2 ones, 1, 0. 1, 1, 1. 3 ones, it is 1, 1. Conditions apply if you write C out and S in the order. Considering C out is MSB, S is LSB, we can write truth table easily, observing number of ones in the inputs. We can write a 2-bit representation of number of ones. 2-bit representation of number of ones. Right, fine. A simple way. Don't follow this because you may be doing a mistake by writing S and C out. If you write S and C out, you are getting that sum expression for carry expression for sum. So don't go with that. Our aim is not to worry about sum. What is it here? We need to worry about carry. So I am erasing this sum. Now we need to understand dependency of carry out on carry input for each and every AB combination. Why? We understand. For each and every combination of AB, what is the dependency of carry out on carry input? If you are observing, when AB is 0, 0, when AB is 0, 0, what is it here? Irrespective of input carry, output carry is 0. Any doubt in that? When AB is 0, 0, when AB is 0, 0, input carry is 0, output carry is 0. Input carry is 1, output carry is 1. That means output carry is 0 irrespective of input carry, not depending on input carry. Irrespective of input carry, output carry is 0. Right? When AB is 0, 1, when AB is 0, 1, what is that here? Input carry is 0, output carry is 0. Input carry is 1, output carry is 1. Once again, when AB is 0, 1, input carry is 0, output carry is 0. Input carry is 1, output carry is 1. So, output carry is input carry itself. Correct? When AB is 0, 1, whatever is there on input carry will be output carry. Input carry is 0, output carry is 0. Input carry is 1, output carry is 1. Yes, output carry is input carry itself. Understood? When AB is 1, 0, when AB is 1, 0, once again, input carry is 0, output carry is 0, input carry is 1, output carry is 1. Once again, output carry is input carry itself. Output carry is input carry itself. Am I right? So, when AB 1, 0 also, whatever is there on input carry is output carry. When AB is 1, 1, input carry is 0, output carry is 1, input carry is 1, output carry is 1. Irrespective of input carry, output carry is 1. Observe one by one. AB 0 0, irrespective of input carry, output carry is 0. When AB is 0 1, when AB is 0 1, so whatever is there on input carry is output carry. When AB is 1 0, again same. Whatever is there on input carry is output carry. When AB is 1 1, irrespective of input carry, output carry is 1. Then, if you are observing in these two cases, when AB is 0 1 or 1 0, what we are observing? Input carry is propagated to output carry. Once again, when AB is 0 1 or 1 0, input carry is propagated to output carry. When is it possible? When AB is 0 1 or 1 0, propagation is going on. What do you mean by propagation? Input carry is propagated to output carry when AB is 0 1 or 1 0. So in these two conditions, input carry will be propagated to output carry when AB 0 1 or 1 0. Then propagation is true when AB is 0 1 or 1 0, that we are representing as A XOR B. Am I right? AB 0 1 or 1 0 unequal. When AB both are 0 1 or 1 0 means both are unequal, propagation is occurring. So P equals to 1 if I consider as a propagation is true, P is nothing but A XOR B. Any doubt in that? P is A XOR B. Why? AB 0 1, P is 1. AB 1 0, P is 1. P equals to 1, propagation is true, which is indicating that AB are 0 1 or 1 0. Now, for sure, output carry will be generated 1 when AB is 1 1. Next case is what? When AB is 1 1, irrespective of input carry, output carry will be generated 1. When AB is 1 1, irrespective of input carry, output carry will be generated 1. That means generation is true when AB are 1 1. Generation is true when AB are 1 1. When AB are 1 1, right, generation is true. So I hope you are understanding these two. What is it here? Propagation is true when AB 0 1 or 1 0. Generation is true when AB 1 1. What do you mean by generation? For sure, output carry will be generated 1. What do you mean by propagation is true? Input carry will be propagated to output carry. Input carry will be propagated to output carry when P equals to 1. P equals to 1 means A XOR B is 1. A XOR B 1 means AB 0 1 or 1 0. Yes, satisfying that. P equals to 1, propagation is true. Generating output carry 1. Compulsory output carry will be 1 when AB 1 1. When AB is 1 1, irrespective of input carry, output carry will be generated 1. Right? After understanding propagation and generation, now let us say what is the conditions for getting output carry 1 with respect to propagation and generation. Once again, with respect to P and G, with respect to propagation and generation, let us say what is the conditions to get output carry 1. Output carry 1. Once again, I am addressing possibilities of getting output carry 1 with respect to propagation and generation. When propagation is 1, will there be output carry 1? When propagation is 1, will there be output carry 1? No. Propagation is 1 is confirming that input carry is propagated to output carry. So, to get output carry 1, input carry also must be 1 when propagation is 1. Propagation is 1 is confirming that input carry will be propagated to output carry. So, to get output carry 1, in this propagation equals to 1 condition, input carry also must be 1. So, P equals to 1 and CI is 1, then output carry is 1. I hope you're understanding. P equals to 1 is not guaranteeing output carry is 1. P equals to 1 is guaranteeing that just propagation is true. What is that? Whatever is there on input carry will be output carry. But what we are looking for? Output carry to be 1. Output carry becomes 1 when P equals to 1 and input carry is 1. Or G equals to 1, output carry 1. Any doubt in that? If G equals to 1, irrespective of input carry, output carry will be 1. That is called generation is true. Compulsory, it is generating. When G equals to 1, generating output carry 1. then no need to worry about that input carry. Yes, G equals to 1, output carry is 1, or P equals to 1 and Ci is 1. So the expression for C out to be 1 is a P and Ci, or G. P and Ci or G. Any questions? P and Ci or G. I hope it is clear. P equals to 1, Ci is 1. When both are 1, output carry will be 1. Or G equals to 1. Or G equals to 1. These are the two cases. Right? From my side, everything is fine. Right? Finally, what is it here? Carry out to be 1. The conditions, if you are observing, P equals to 1, Ci is 1, or G equals to 1. So, while estimating C1, I can use A0, B0, C0. While estimating C2, A1, B1, C1. While estimating C3, A2, B2, C2. While estimating Cn, what we can say? Pn minus 1, Cn minus 1 plus Gn minus 1. Take it correctly. While estimating Cn, see C1 from A0, B0, C0. That is the reason we can say that n minus 1 bits. So C2 from this, C3 from this. So to estimating Cn, Pn minus 1, Cn minus 1 plus Gn minus 1. In this, C1 is equals to what we can write? P0, C0 plus G0. P0, C0 plus G0. Right? What is P0? A0 XOR B0. What is G0? A0 B0. P is nothing but 2 input XOR. G is nothing but 2 input AND. And what about C2? P1 C1 plus G1. Yes, P1. What is C1? P0 C0 plus G0 is C1 plus G1. So P1 P0 C0 plus P1 G0 plus G1. What about C3? P2 C2 plus G2. P2, what is C2? P1 P0 C0 plus P1 G0 plus G1. Expand this. P2 P1 P0 C0 plus P2 P1 G0 plus P2 G1 plus G2. What are these? C1, C2, C3 expressions. What is P? 2 input XOR. What is G? 2 input AND. 2 input AND. So P is nothing but XOR, G is nothing but AND gate. If you are observing, when number of bits has been increasing, complexity of additional circuit is also increasing. When complexity of additional circuit is increasing, propagation delay of this additional circuit is also increasing. Understand point correctly? When number of bits is increasing, if I have one more bit, C4 will be bigger expression than this. Bigger expression than this. So if you have that one more bit, expanding more, and one more bit, and so and so. If you are increasing number of bits, complexity of additional circuit is also increasing. Complexity of additional circuit is also increasing. Then propagation delay of additional circuit is also increasing. Then what happens here? Instead of looking ahead, it may be looking back. Why? Propagation delay of additional circuitry may be exceeding carry rippling time. Because complexity of additional circuitry is increasing, then obviously propagation delay is increasing. When propagation delay is increasing, instead of saving time, it may be taking more time. That is the reason we say that carry look ahead adder may save time for smaller number of bit additions. When larger number of bit addition, if you are observing, it may not be saving time because carry estimation time is exceeding carry propagation time. So previously what we have used a rippling carry or carry propagating from one stage to another stage. Instead of that, if you are generating carry for each and every full adder, carry estimating from different circuits, then carry estimation time may be exceeding carry rippling time. So it has to we observed whether this delay of this higher order bit or higher order bit carry time is lesser than n minus 1 TC. There we can save time. So in a given technology, propagation delays are provided for each and every logic gate. And what is the propagation delay when we are implementing ripple carry adder? So there we can estimate n minus 1 TC. We can estimate propagation delay of this logic circuit. If propagation delay of logic circuit is lesser than n minus 1 TC, there it is looking ahead because it is saving time. Otherwise, it is not saving time. We cannot use that CLA. Carry look ahead adder. So what we are analyzing here? CLA. Carry look ahead adder. What we are analyzing here? CLA. Carry look ahead adder. So look ahead adder may be becoming look back adder, or maybe it may not be saving time as expected. It may not be saving time as expected. When number of bits is increasing, additional circuitry complexity is increasing. So when complexity is increasing, propagation delays are increasing. When propagation delays are increasing, so it may be taking more time than ripple carry adder. So if it is saving time, look ahead. Otherwise, it's looking back. So there we don't use that CLA. Carry look ahead adder. Carry look ahead adder. Right. In all these adders so far we have discussed, we have parallel pins to apply inputs, parallel pins to observe the result. Once again, in all these adders so far we have discussed, there are parallel pins to apply inputs, there are parallel pins to observe the result. So these are called parallel adders so far we have discussed. Now we are going to discuss a serial adder. Serial adder. Serial adder. Serial adder. What do you mean by serial adder? It is not a parallel adder, in which we are applying bit by bit serially. That means we are not applying all the bits at a time. It is not possible to observe the result also on parallel pins. So in this we are applying bit by bit serially. The result are some also producing bit by bit serially. Serially we are applying bit by bit. Serially it is producing output also. Just think of this. Right? I'll be back in 2 minutes. Yes, I'm back. So now serial adder in which we are applying bit by bit serially. We are applying bit by bit serially. So it is producing bit by bit serially the sum. So when you are applying that inputs bit by bit serially, and it is producing sum also bit by bit serially. So it is named as a serial adder. It is named as a serial adder. Then what we can do here, I don't need to use n full adders for n bit addition because I don't need to have the parallel pins. I don't need to have parallel pins. Then what is that here? I am applying bit by bit serially means I can reuse one full adder for n bit addition. What is it here? In serial adder, I can reuse one full adder for n bit addition. One full adder for n bit addition. Once again, what is it here? In serial adder, I don't need to use n full adders for n bit addition. I can use one full adder. I can reuse for n bit addition. For n bit addition. So let us see what is it here. How we can do that. What is it here? I don't need to use n full adders for n bit addition. I can reuse one full adder for n bit addition. How is it possible? Let us see. So one full adder for n bit addition. This is a full adder in which it is possible to accept inputs A, B, and Ci. Here sum and carry out. Sum and carry out. So in this, what we say here it is A, here it is B, and here it is input carry Ci. It is producing carry out, and here it is sum. First we apply A0, B0, C0, producing S0 and C1. Next we apply A1, B1, C1, and producing S1. A2, B2, C2, producing S2, and so and so. That is bit by bit serial it is producing. First of all, we are applying A0, B0, C0, producing S0 and C1. According to our earlier discussion, if I am applying A0, B0, C0 as inputs, producing S0 and C1. When we are applying A1, B1, the C1 should be applied here. Where is that C1? Output carry of previous bit addition. Then what I can use? What I'm doing here? So when A1, B1 is applied, the C1 is here because when A0, B0, C0 is applied, producing S0, here it is C1. That C1 must be applied as input carry when A1, B1 is applied. But if you are feeding back immediately, is causing a problem. What is the problem? Let us see. For example, A0, B0 is 1, 1 I have applied and C0 is 0. For example, what may happen? Let us understand. What happens here? 1, 1, 0 inputs producing sum is 0, carry is 1. Correct? When 1, 1, 0, A0, B0, C0 are applied, producing S0 is 0 and C1 is 1. And if you are applying immediately, the same carry will be considered as input carry for the same bits. Again, it is producing sum is 1. I hope you are understanding. If you are feeding back immediately, instead of waiting for applying next bits, it may be added to the same bits. That's a problem. Once again, example I consider 1, 1, 0 was there. Now it is producing sum is 0, carry is 1. As you are applying output carry as input carry immediately, then it is using for same bits, then it is giving a wrong result. That means it should not be fed back immediately. Then what should I do? Generally, I'm getting answers like this. What I do, instead of applying immediately, what people have been suggesting me is apply a delay. How much delay? Is it best case or worst case? Again, delays are not fixed because different input combinations are producing outputs, sum and carry out in different times. Then how much delay must be there? Best case or worst case or average, all this will be failing. Then what can I do? First of all, you should know how we are applying A0, B0, How we are applying next A1, B1, A2, B2, and so and so. How are you going to apply bit by bit serially at input side? Are you hiring two persons? No. I want to automate this. For that, what we do here is guess we are using a shift register. It is a shift register. A is a shift register. And here also B is a shift register. B is a shift register. A is a shift register. B also a shift register. What is it here? First we apply A not B not. Then it is shifting right. Then A1 B1 shifting right A2 B2 and so and so. We are going to apply n bits. Right? If I am using n bit shift register, I can apply bit by bit serially. So when the contents of register are shifted right, the next bits will be applied as inputs. That means the reference point where I am applying next bits is a clock edge occurrence. What is there? Clock edge occurrence. Reference point where I am applying next bits to the full adder is a clock edge occurrence, because shift operation is occurring when clock edge is occurring. In a shift register, shift operation can be performed when clock edge is occurring. When clock edge is occurring. So when clock edge is occurring, the output carry must become input carry. The output carry must become input carry. So whenever shift operation is occurring, that means whenever clock edge is occurring, output carry must become input carry. Means instead of using a combinational delay element, I can use a sequential delay element, which is a delay flip flop. What is it here? Delay flip flop, which is a delay flip flop. Instead of using combinational delay element, we can use D flip flop. We can use D flip flop. What happens here? When clock edge is occurring, whatever we are applying on D is becoming Q. Is nothing but whatever the output carry is there is becoming input carry when clock edge is occurring. That means whenever next bits are applied for this full adder, there itself output carry is shifted to input carry. So Q becomes D when clock edge is occurring. So D is ready, but D will not be propagated to input carry, or output carry will not be propagated to input carry immediately. When is it propagated to input carry? When clock edge is occurring. When clock edge is occurring, next bits are applied here on shift registers. So if I am using clock for this shift register, clock for this D flip flop, then we can achieve expected synchronization among inputs. Are you understanding? Yes. When shift operation is occurring, when clock edge is occurring, output carry is also shifted to input carry. That means we are achieving synchronization among all the inputs with respect to clock. Because we have to use clock. Why? We need to apply bit by bit serially, means shift register is required. Shift register is there means clock is there. So by using same clock as a clock here for this D flip flop, we can achieve synchronization among all the inputs. Yes, inputs are satisfied. What is it here? Inputs are applied synchronously, bit by bit, serially. But we have another problem here. What is that? A naught, B naught, C naught applied, producing S naught. Next, A1, B1, C1 will be applied, producing S1. When A2, B2, C2 is applied, producing S2. When S1 is produced, S naught was there, overwritten by S1. When S2 is produced, overwriting S1, so and so. So and so. That means after n clock cycles, n bit addition will be completed. But only nth bit will be available on this sum. That is the reason we have to use a shift register to store sum also. Sum again, n bit shift register required. So after n clock cycles, the addition will be completed. So in this shift register, n bit sum will be available. N bit sum will be available. I hope you are following. Are you there? So to apply inputs, we are using a clock. To store the result also, we are using a shift register. In n clock cycles, n bit addition will be completed. N bit addition will be completed. Yes. Yes. Everyone may be getting, some of you may be getting doubt. When we are suggesting, you will understand that after getting into sequence circuit, please hold on. So as we are studying adder circuit, we are completing serial adder. So everyone might be getting the doubt, right? What is the doubt? Are we studying combination circuit or sequential circuit? Yes, it is a sequential circuit because it is using flip-flops and registers, means it is having a memory element. Then it is a sequential circuit. It is not a fully combinational circuit. It is not a fully combinational circuit. It is a sequential circuit. So serial adder is a sequential circuit. It is not a fully combinational circuit. Yes. Yes. Right. By using clock only we can apply. Ankur Kashyap, if you are not applying, if you are not using shift register here, on this port, bit by bit it is producing. S0 is produced. When S1 is produced, where is that S1, where is that S0? After n clock cycle, I need n bit of sum. From where I can get that n bit sum? If I use only one terminal, there it is overwriting bit by bit. Kashyap, Ankur Kashyap, right? That's what I've been saying, Bhaskar. It is not a fully combinational circuit, it is sequential circuit. It is sequential circuit, right? So why do we need S shift register is after n clock cycle, n bit addition will be completed. But after nth clock cycle, without shift register, if you are not storing the bit by bit, it is produced. On this terminal, we have only one bit, last bit only. But I need n bit sum. To get that n bit sum, I need to store bit by bit, it is produced. Bit by bit, it is produced. Manikanta. Yes, you are going to understand more, right? Manikanta. Yes. People are in right way in understanding the concept. Yes. So how much time it takes to complete the addition? That is also important. How much time it takes to complete the addition? Bhaskar, the points which I raised, you are asking again. If I'm using combinational delay here, how much I need to provide? Because here sum and carry out, are they produced with best case input conditions or worst case input conditions? We don't know. So how much delay I need to provide here for different combinations of inputs, different delay. It must be a variable delay. That is the reason it is not possible. It is not possible. That is the reason, irrespective of delay, it is produced outputs. It will be applied at common point of time when clock edge is occurring. So a reference point where I'm applying all the inputs. All the inputs. So Bhaskar, I raised the same doubt and I explained. Please focus on my words. Yes, Gopal Krishna, wait. So if I'm using a clock, with respect to clock, let us see how much time it takes to complete a n-bit addition. So first we apply here at first clock edge occurrence, before occurrence, A0, B0, C0. Here A2, B2, C2. Here A3, B3, sorry, A2, sorry, A1, B1, C1 here, A2, B2, C2, here A3, B3, C3. So by this time addition will be completed. That means 1, 2, 3, 4. So applying 4 bits, but to complete that addition, it takes how many clock cycle? 1, 2, 3, 4 clock cycles for 4-bit addition. If it is n-bit addition, T n-bit is equals to n clock cycles, n TCLK. What is TCLK? The clock period we are using here. T clock period. T clock period. Right? But here you need to provide sufficient time to complete the addition in this available time. So available time to complete the operation is from this edge to this edge, 1 clock cycle. 1 clock cycle. It is a 1 clock cycles. In one clock cycle, all the operations must be completed. What is that? From the clock edge occurrence, shift operation is started. Shifting registers cannot be in zero time. That means it takes some time to shift. No need to understand everything. I'm going to address each and every parameter which I'm mentioning here in sequential circuits. And after shifting only, input should be applied to the full adder. Full adder is taking a delta time to produce the output. Again, this produced output must be applied as inputs. That means it is needing setup time. So here flip-flop delays, here full adder delay, here setup time the flip-flop. So finally, forget about these two parameters. Forget about these two parameters. So what is delta? Full adder delay. That means the clock period must be greater than delta. Do you accept this? Forget about these two parameters. Why are these? I will explain later. Until that, just have a just understand that there will be two more parameters which you need to include in this clock period. Final conclusion is the clock period TCLK is greater than delta. Will there be any doubt? Because after applying inputs, addition should be completed. For addition, it is taking delta time. What is delta? Full adder delay. To apply the inputs, it is taking time. Produced outputs must be ready sometime before itself, before occurrence of next clock edge. So all this I will be clearing later. Until that, hold on. So at this moment, what we can say? TCLK greater than delta. TCLK greater than delta. That means T n bit is greater than n delta. T n bit is greater than n delta. Once again, final thing is to complete one bit addition in this serial adder, it is depending on clock period. The clock period also must be sufficient to complete the operation, which is nothing but applying inputs. Addition is completed, then produced result also must be meeting some requirement at next clock edge occurrence, which is nothing but setup time. So what are these parameters? I will explain later. But for this moment, we have two more parameters should be included, or delta must be lesser than one clock period, or TCLK must be greater than delta. If TCLK is greater than delta, n bit adder delay Tn bit is greater than n delta. Greater than n delta. Correct? So finally, what is it here? First one is what? See, comparisons if you are observing. First one, parallel adder, n delta. Next one is what? N minus 1 TC plus maximum of TS comma TC, which is optimized than n delta. Then next one is what? CLA lesser than this. Lesser than this, right? Am I right? So CLA is taking lesser than ripple carry adder. Now what is it here? Greater than n delta. Which one is that? Serial adder. So parallel adder, parallel ripple carry adder, carry lookup adder, serial adder. Which one is slowest now? Which one is slowest? Serial adder. Which one is fastest? CLA. It is CLA. It is a serial. It is a ripple. Simply parallel. Simply parallel adder. Simply parallel adder. Right? So it is a parallel adder. It is optimized in ripple carry adder. It is minimized in CLA. Now it is greater than parallel adder means it is a serial adder is slowest. Fastest is what? CLA. Among all the adders so far we have discussed, the serial adder is slowest. Fastest is what? CL. Whenever it is saving time, it is CLA only. So whenever it is required to compare the speed list 1, list 2, match the following, then you can compare this way. What is it here? Serial is slowest, fastest is CLA. Next is what? Speed. Speed, high speed CLA, and next speed is ripple carry adder, next is parallel adder, next is serial adder. This is a order. This is order. That's what we have discussed about a serial adder. So yes, serial adder is not fully combinational circuit, it is sequential circuit, and it is the slowest adder. the time required to complete n bit addition is n clock cycles. Clock period must be greater than full adder delay. Yes, it is greater than n delta, means it is the slowest adder so far we have discussed. So far we have discussed. Right. That is a adders which we have in our syllabus, which we need to cover, which we need to understand. Yes. Now, right, who is that rising hand? Prashant, Bhima Shankar. Prashant, Bhima Shankar. Right. We discuss all your doubts, all your queries. Right. Carry is not n bit. Ankur Kashyap. Why do I need shift register in the carry? Are we applying that n bit carry at a time? We are getting bit by bit, right? So there, one flip flop is sufficient instead of a register. If required, we use. Otherwise, it is not required. We neglect. Raghavendra. Right. In a processor, after addition, what we do? Accumulator is getting result. Then carry flag is set or reset depending on condition. Raghavendra. What we do with the carry means, if required, we use. Otherwise, it will be there in the carry flag. Yes, without this clock or shift registers, it is not possible. It is not possible. Ankur. Right? In clock, Ashutosh. That's what I mentioned. TFF. In the clock itself, I mentioned it is TFF first, then delta. Right? Ashutosh. Shift register flip-flop delays are considered. Right? Not very important, Praneeth. Not very important. Just know the functionality. Right. After this, now, right, stop typing, listen. Now, n bit subtract. For binary subtraction, we have two methods, 2's complement and 1's complement method. Which one is preferable? Which one is preferable? 2's complement method, right? 2's complement method is preferable. For binary subtraction, we have two methods, 2's complement and 1's complement method. So in 2's complement method is preferable. In 2's complement method, what is the first step? A plus 2's complement of B. Correct? First step is what? A plus 2's complement of B. So let me take that sum is equals to A plus 2's complement of B means B bar plus 1. Any doubt? A plus B bar plus 1. A plus 2's complement of B. A plus 2's complement of B. That is nothing but B bar plus 1. If you are observing, A plus 2's complement of B is first step. So if I say sum is equals to A plus 2's complement of B is what? Complementing B, adding 1 to the LSB. Right. In second step, what we are doing? If carry out is 1, if carry out is 1, what is that here? Difference is equals to sum. Am I right? If carry out is 1, discarding carry, sum is the result, difference. Correct. If carry out, final carry out is 1, discarding that carry, sum is the difference. Else, what is difference? What is difference? 2's complement of sum is nothing but a complement of sum plus 1. Correct? What is 2's complement of sum? Complement of sum plus 1, LSB. When carry out, final carry out is 1, discarding carry, sum is the difference. When final carry out is not 1, that means else means carry out is not 1. Carry out is not 1 means carry out is 0. Difference is what? 2's complement of sum. 2's complement of sum, which is nothing but a complement of sum plus 1. Let us see how to get this using n-bit adder. Using n-bit adder. Observe clearly what we are doing. N-bit adder, example 4-bit adder. I am explaining with respect to 4-bit. So now here we are applying, what is it? A3, A2, A1, A0. What I am applying here? B3 bar, B2 bar, B1 bar, B0 bar, complement of B. And what else will be there? C0. Let me make C0 is 1. Now what this adder is performing now? A, B bar, 1. So A plus B bar plus 1. Is it completing first step? So A I am applying directly. Instead of applying B, I am applying B bar. Instead of applying C0, 0, we are applying C0 is 1. So A plus B bar plus 1. B bar plus 1 is what? 2's complement of B. A plus 2's complement of B. Yes, first step is completed. Which may be producing output carry 1 or 0. Which may be producing output carry 1 or 0. Depending on this output carry, for example, if you have here S3, S2, S1 is not sum. So whether should I consider sum as difference or 2's complement of sum is decided by carry out is 1 or 0. Let us see how it can be completed. The next step. Listen carefully. XOR gates I am using. Second operand is grounded. So, and here again 4-bit adder. Now one input is a complement of this carry out. Now here we are applying this. Let me see, it is a S3, S2, S1, S0 sum. Right. Let us see what is happening here. So one by one conditions, if you are observing, first condition, if C out is 1, what we are expecting at difference? This sum which must be there at difference. When C out is 0, here we need to get a 2's complement of sum. Is nothing but complement of sum plus 1 we are expecting. Yes. So when C out is 1, output of inverter is what? 0. What will be output of XOR gates? What will be output of XOR gate? XOR gate, if one input is 0, output is X. XOR gate, one input is 1, output is X bar. Output is X bar. I hope you are understanding. When one input is 0, output of XOR gates will be what? S3, S2, S1, S0 only. Then that means it is sum second operand is 0, and we are getting input carry also 0. Then some bits are there, 0 is there, and 0 is there. That means what we are getting here? Sum only. See, when we are applying S3, S2, S1, S0, and here we are getting 0. One input is 0. Other inputs are some bits. What is the output of XOR gates? S3, S2, S1, S0 only, because we are using this one. So here we are getting S3, S2, S1, S1 means sum plus 0 plus input carry is 0. Then what we get here? Sum. Right. When Cout is 0, then what we get here? Here it is 1. When here it is 1, output of XOR gates will be S3 bar, S2 bar, S1 bar, S0 bar. Am I right? That means complement of sum. Here one operand is 0, and what we get here? 1. So complement of sum plus 0 plus 1. What we get here? Complement of sum plus 1, which is 2's complement of sum at difference. And Cout is 0. When Cout is 1, we are getting sum. When Cout is 0, 2's complement of sum. When Cout is 0, it is 2's complement of sum, because complement of sum plus 1. When Cout is 1, here it is 0, here we are getting sum, here it is 0, here it is 0. It is a sum itself. Yes, n-bit binary subtractor using n-bit adder. N-bit adder. Example, we consider 4-bit subtraction. 4-bit subtraction. Right? Don't get saturated. Try to understand each and every point, because by giving the circuits, they may be asking what is the operation it is performing. So if you analyze these type of questions, you may be in a position to answer questions, because sometimes they may be adding some number here, and they may be providing some information or multi-steps. They may be giving big circuit. They may be asking you to say what is the result. What is the result? There we need to understand correctly. If you are analyzing these type of questions again, yes, you'll be getting such a analysis. So next, let us consider one more circuit. I'm moving to next slide. Moving to next slide. Yes. Now let us see one more circuit. Just a minute. XOR gates. A3, A2, A1, A0, and here it is C0. So in this circuit, we have control signals only K and C0. We don't have control on A, B, and other inputs. Whatever we have inputs, we don't have control on that. So irrespective of A3, A2, A1, A0, B3, B2, B1, B0. By changing K and C naught, we can perform some operations. What operations it can perform? Let us see what is the function it can perform for each and every possible K and C naught. K and C naught. For each and every possible K and C naught, what is the function it is performing? Let us see. When K equal to 0, output of XOR gates will be B3, B2, B1, B0. When K equals to 1, output of XOR gates will be B3 bar, B2 bar, B1 bar, B0. Once again, this control signal is controlling whether we are getting B or B bar as operand. This K control signal is controlling the other input is B or B bar. And here C naught can be 0 or 1. So we can have this K and C naught are controllable using these control signals. What are the operations it can perform? Let us see. When K equal to 0, C naught is equals to 0. K equal to 0 means we are getting B, A, B, and here C naught is 0. That means A plus B plus 0. Why you are saying it is B? As K is 0, output of XOR gate should be B3, B2, B1, B0. Means there is B itself, A, B, and 0. The operation is A plus B plus 0. It is A plus B. A plus B. For each and every combination of K and C naught, I am observing what is the operation is performing. So K is 0, C naught is 0. K is 0, C naught is 0. Then what we get here? B, A plus B plus 0 is A plus B. So if it is K is 0, C naught is 1. When K is 0, it is B, it is A plus B plus 1. Operation is A plus B plus 1. Add with carry. Right? Or add with the extra 1. Now, another operation. What is it here? When it is 1, 0. If it is 1, 0, what we get? If it is 1, what we get here? B3 bar, B2 bar, B1 bar, B0 bar. It is B bar. A, B bar, it is 0. That means A plus B bar. A plus B bar. Am I right? When K equals to 1, here we are getting B bar. A plus B bar plus 0. It is A plus B bar. Here it is 1 and 1. Then what we get? K is 1, C naught is 1. Then what we get here? As K is 1, it is B bar, it is A plus B bar plus 1. A plus B bar plus 1 is nothing but A plus 2's complement of B. The result can be used for A minus B. Am I right? Observe correctly. Here when K equals to 1, C naught is 1, A plus B bar plus 1. Why it is B bar? As K is 1, here we are getting complement of other input. B3 bar, B2 bar, B1 bar, B0, it is B bar. A plus B bar plus 1, which is A plus 2's complement of B, which is A minus B, which is A minus B. The result can be used for A minus B. So we can name it as a controlled adder and subtractor. By using control signals, Sweta Sharma, right? By using control signals, we can perform the operation, right? Different operations. So in that, if we are observing A plus B, right? A plus B plus 1, A plus B bar, A plus B bar plus 1, A plus B bar plus 1 is A plus 2's complement of B. The result can be used for A minus B. I'm not saying that it is A minus B. I'm not saying it is A minus B. The result can be used to get A minus B, to get A minus B. So this is what n-bit subtractor, controlled adder and subtractor. Controlled adder and subtractor. Moving to next slide. Now, okay, let me take a small break, then we continue. After 15 minutes from now, we'll resume. Welcome back. Here it is a plus b bar plus 1, which is a plus 2's complement of b. It is not a minus b. The result can be used to get a minus b. That's what I mentioned. So the result can be used for a minus b. People are getting doubt about this. The reason I'm mentioning that it is a result can be used for a minus b. Right? Now, let us see a conversion from binary to gray. For example, if it is required to convert from binary to gray, a simple conversion, binary to gray. That means binary inputs, if I consider B2, B1, B0, 3-bit binary if I say, and 3-bit gray, G2, G1, G0, G2, G1, G0. So binary order is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 1, 1. 0, 0, 0 to 1, 1, 1. What is gray order? 0, 0, 0. Next, 0, 0, 1. Next, 0, 1, 1. Am I right? 0, 1, 0. Next, 1, 1, 0. Next, 1, 1, 1. Next, 1, 1, 1, 0, 1. Next, 1, 0, 0. We know that 0, 1, 3, 2, 6, 7, 5, 4. That we know already. That we know already. Find Boolean expression for outputs in terms of input variables. So what can we give here is let me give input combination numbers 0, 1, 2, 3, 4, 5, 6, 7. Then find Boolean expression for outputs in terms of input variables. Find Boolean expression for outputs in terms of input variables. What do you mean by this? G2 is equals to sigma m of 4, 5, 6, 7. 4, 5, 6, 7. What about G1? Sigma m of 2, 3, 4, 5. 2, 3, 4, 5. What about G0? Sigma m of 1, 2, 4, 5, 6. 1, 2, 5, 6. Find Boolean expression for G2, G1, G0 in terms of B2, B1, B0. Let us see using three variable K maps. If you find Boolean expressions of G2, G1, G0 in terms of B2, B1, B0. Here B2, B1, B0, 0, 0, 0, 1, 1, 1, 1, 0. First, if I go for G2, what is here? 4, 5, 6, 7. Then this is a grouping. We are getting G2 is equals to B2. Similarly, for G1. Similarly, for G1. Here it is B2, B1, B0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. So 2, 3, 4, 5. Then it is one grouping, second grouping. Then G1 is equals to B2 bar B1 plus B2 B1 bar, which is B2 XOR B1. And, one more K map for G0. Not required all this once we are understanding what is exactly expression, sir, how to proceed. That to confirm that only for the students who have been doing this first time, I am explaining this, sir. So what we have here, what we have here, 1, 2, 5, 6, right? 1, 2, 5, 6. Then this is one grouping, this is another grouping. So what we get here, G0 is equals to B1 bar B0 plus B1 B0 bar, which is a B1 XOR B0. B1 XOR B0. So this is a expressions for G2, G1, G0. So let me write the circuit itself. If I have a B2, B1, B0. G2 is equals to B2. G1 is equals to B2 XOR B1. G0 is equals to B1 XOR B0. Correct? That's what we are getting. G2 is equals to B2. G1 equals to B2 XOR B1. G0 is equals to B1 XOR B0. That's what we are writing. If it is 4-bit, can you guess what can be that? G3 is equals to B3. G2 is equals to B3 XOR B2. G1 is equals to B2 XOR B1. G0 is equals to B1 XOR B0. B1 XOR B0. Otherwise, if I have n bits, what we can write? Bn minus 1, Bn minus 2, Bn minus 3, so and so, B2, B1, B0. Then what is this? MSB as it is. Then XOR of these two bit we are getting as a next bit Gn minus 2. XOR of these two is a Gn minus 1. So and so. Then again XOR here with previous bits. We get here G2. Then G1. Then again XOR is G0. This is what we do. Successive bits we are XORing to get a gray equivalent of a binary. Gray equivalent of binary. So what we are doing here? Binary to gray conversion. Binary to gray conversion. So bit by bit, what is it here? MSB as it is. To get remaining bits, take XOR of successive bits. Take XOR of successive bits. For example, if I say 1 0 1 1 0 1 1 1, this is a binary. What is the gray equivalent of this? Simply, what is it here? 1 as it is. XOR of these two, 1. XOR of these two, 1. XOR of these two, 0. XOR of these two, 1. XOR of these two, 1. XOR of these two is 0. XOR of these two. That is a gray equivalent of given binary. What we are doing? MSB as it is. XORing of successive bits. To get remaining bits, XORing successive bits. XORing successive bits. So MSB as it is, to get remaining bits, take XOR of successive bits. Correct? That is binary to gray. Now if it is a gray to binary, let me complete that also. Gray to binary. What is it here? G2, G1, G0 are inputs, B2, B1, B0 are outputs. That is 3-bit gray to 3-bit binary. What is gray sequence? 0, 0, 0, 0, 0, 1, 0, 1, 1, next 0, 1, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 0, 0. That is a gray sequence. What will be the binary? 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Now, what is input combination numbers? 0, 1, 3, 2, 6, 7, 5, 4. Check it correctly. Combination numbers is different. It is not 0, 1, 2, 3, 4, 5, 6, 7. So 0, 1, 3, 2, 6, 7, 5, 4. Now, B2 is equals to sigma m of what we get here 6, 7, 5, 4. We can write 4, 5, 6, 7. What about B1 sigma m of what we have here 3, 2, 5, 4, which is 2, 3, 4, 5. What about B0 sigma m of what we have here 1, 2, 7, 4. 1, 2, 4, 7. Now use K-map to find minimal expressions of B2, B1, G0 in terms of G2, G1, G0. So in terms of G2, G1, G0, let us see how the expression. Once again, variables are G2, G1, G0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 4, 5, 6, 7. Then what we are getting here? B2 is equals to G2. One more K-map for B1. G2, G1, G0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. So 2, 3, 4, 5. Once again, these two. What is it here? B1 is equals to G2 bar G1 plus G2 G1 bar. Is nothing but G2 XOR G1. Also can be written as G2 equals to B2. B2 XOR G1. B2 XOR G1. Now, one more. What we have here? G2, G1, G0. 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. What we have here? 1, 2, 4, 7. As we know already, 1, 2, 4, 7 is what? 3 input XOR. 1 is 0, 0, 1. 1 input is 1. 2, 0, 1, 0. 1 input is 1. 4, 1, 0, 0. 1 input is 1. 7, 1, 1, 1. 3 inputs are 1. 1 input is 1. 1 input is 1. 1 input is 1. 3 inputs are 1. 1 input is 1 or 3 inputs are 1. That means odd number of ones, then output is 1, which is a 3 input XOR. 3 input XOR. So B0 is equals to G2 XOR G1 XOR G0. G2 XOR G1 is nothing but B1. So B1 XOR G0. B1 XOR G0. G2 XOR G1 XOR G0. G2 XOR G1 is nothing but B1. B1 XOR G0. B1 XOR G0. So what can be the circuit is if B2, B1, B0. Sorry. Inputs is now G2, G1, G0. G2, G1, G0. Here we get B2 is G2 itself. Then XORing with B2, which is G1, is giving B1. And also again XORing, what is it? B1 XOR G0, which is a B0. Which is B0. If it is 4-bit, let me write a gray to binary. B3 is equals to G3. B2 is equals to B3 XOR G2. B1 is equals to B2 XOR G1. B0 is equals to B1 XOR G0. Check it. So if it is n bits, what can we do? Let us see. Gn minus 1, Gn minus 2, Gn minus 3, so and so, G2, G1, G0. So MSB as it is, no doubt it is Bn minus 1. Now XORing these two, resulting Bn minus 2. Now XORing with previous binary and respective gray is giving that respective binary. So and so XORing with the previous binary, it is a B2. Again, your B2, G1. That is a gray to binary. Gray to binary. If gray sequence is given, we want to get a binary sequence. That's what we are doing. Moving to next slide. If this is gray, what will be the binary sequence? Check it correctly. What we are getting here? 1. 1 XOR 1 is 0. 0 XOR 0 is 0. 0 XOR 0 is 0. 0 XOR 1 is 1. 1 XOR 1 is 0. 0 XOR 1 is 1. 1 XOR 1 is 0. That is a binary sequence. Simply writing same MSB and here it is XOR between these. Between these two XOR and between these two XOR. Next bits. That's what we are doing. 1 1 XOR next bit, 0 0 XOR next bit, 0 0 XOR is next bit, 0 1 XOR is next bit, 1 XOR 1 is next bit, 0 XOR 1 is next bit, 1 XOR 1 is 0 next bit. Binary to gray, gray to binary. Right. That is a code conversion from binary to gray and gray to binary. Gray to binary. Now, let us see one more. BCD to XS3. BCD to XS3. First of all, let us see what do you mean by BCD. Binary coded decimal. Binary coded decimal. What is binary coded decimal? Each and every decimal digit is represented with a 4-bit binary vector. Why we are using 4 bits? To differentiate 10 possibilities 0 to 9. To differentiate 10 possibilities 0 to 9 are differentiated with 4-bit vectors 0 0 0 0 to 1 0 0 1. That is a natural BCD. Once again, binary coded decimal. Decimal digits are coded with binary vectors with predefined rules. If I say natural BCD, natural binary weights are used for representing decimal digits, which is nothing but 8421. Why? 2 power 0, 2 power 1, 2 power 2, 2 power 3 are weights for 4-bit representation. So natural binary weights are used for representing decimal digits 0 to 9. So it is called natural BCD. Once again, BCD, binary coded decimal. Each and every decimal digit is coded with binary vector. We are using 4-bit vectors to code decimal digits. The reason is 10 possible symbols are differentiated with 4-bit vectors. For differentiating 10 possibilities, we are using 4-bit vectors. So in that, if you are using different rules, we are getting different BCDs, different BCDs. First one is a BCD. In general, we say that BCD means natural BCD. If it is not mentioned any rules for that, then simply we say that natural BCD. What is it? XS3 BCD. Natural BCD plus 3 is XS3 BCD. And we can have 5421 BCD, 2421 BCD, right? Different 63 plus 1 minus 1 BCD, different BCDs. Right? So we have a different codes for representing decimal digits 0 to 9. So if I say natural BCD, decimal digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are decimal digits 0 to 9 are coded with binary vectors. 0 is 0, 0, 0, 0. And what is 1? 0, 0, 0, 1. What is 2? 0, 0, 1, 0. What is this BCD? 8421 BCD. Or 2 power 0, 2 power 1, 2 power 2, 2 power 3. Remember this. So natural BCD I am writing is nothing but 8421 or weights. Using 8421 weights, I am representing 0 to 9. What is 3? 0, 0, 1, 1. What about 4? 0, 1, 0, 0. What about 5? 0, 1, 0, 1. What about 6? 0, 1, 1, 0. 7, 0, 1, 1, 1. 8, 1, 0, 0, 0. 9, 1, 0, 0, 1. 1, 0, 0, 1. This is a natural BCD. What about XS3 BCD? Natural BCD plus 3. 0 in XS3 is a 0, 0, 1, 1. 1 in XS3 is a 0, 1, 0, 0. 2 in XS3 is a 0, 1, 0, 1. 3 in XS3 is 0, 1, 1, 0. Plus 3. Next, what is it here for? 0, 1, 1, 1. Next, 1, 0, 0, 0. Next, 1, 0, 0, 1. Next, 1, 0, 1, 0. Next, 1, 0, 1, 1. Next, 1, 1, 0, 0. These are XS3 BCD. So what is the rules behind the XS3 is a natural BCD plus 3 is XS3. Ganeshwari, binary coded decimal means the digits 0 to 9 we are representing. It is not 9, it is 0 to 9, 10 symbols. So in binary, in decimal, the possible symbols, one symbol, one digit is a 0 to 9 only, no other possibility. Decimal digits can be 0 to 9 only. That is the reason we are using 0 to 9 representation with different rules. Ganeshwari, right? Natural BCD. Now here it is XS3. So natural BCD plus 3 is XS3. So each and every representation 0 to 9 is represented with 0, 0, 1, 1, 2, 1, 1, 0, 0 in XS3. What is the rules for XS3? Natural BCD plus 3 is XS3. Natural BCD plus 3 is XS3. Right. Now, listen carefully. We need to understand some properties for objective exams. Right. For conventional, we can go with again minimization and all minimal expressions of each and every output that we do with few examples. But what we need to understand properties of these BCDs is for competitive exams or for objective exams. What we need to learn, let us see. Right. So here natural BCD, which is also named as a 8421 BCD. What are 8421 weights? What are 8421 weights? So using weights, we are representing decimal digits 0 to 9. So natural BCD is what? Weighted BCD. Check it correctly. What is it here? Natural BCD is weighted BCD. Why? Using 8421 weights, I am representing 0 to 9 decimal digits. Wait, what is the advantage of XS3 we are going to do? Please wait. Prithviraj, let me proceed with my discussion, sir. Right, I will answer your doubts, sir. Please wait. So, what is it here? 8421 BCD means 8421 are weights. Natural BCD is 8421 BCD. 8421 means these are weights. It is called weighted BCD. Now, what about XS3? It is non-weighted. It is Non-weighted. Why? I cannot use any weights for getting decimal equivalent is representing using summation of weighted values. What is the rules we have used for XS3? Natural BCD plus 3 is XS3. Natural BCD plus 3 is XS3. By adding 3 for natural BCD, we are getting XS3. Rules behind XS3 is natural BCD plus 3. So I am not using any weights for these positions. So it is non-weighted. It is non-weighted. What is it here? XS3 is non-weighted BCD. Natural BCD or 8421 BCD is weighted BCD because using weights only, we are representing decimal digits. We are representing decimal digits. Manikanta. After 9, if I have 10 in natural BCD, natural BCD means binary coded decimal. So we are representing with the each and every digit with 4-bit vector. This is now 10. Let me proceed. I will give you clarity with examples. Not only this, I'm going to address one important topic also with respect to this BCDs. Please hold on. So yes, sir. Whenever you are getting doubts, give me a chance. Wait. I will answer your doubts. Right? Please, after 9, 10 can be represented with the 1, 0. So each digit is coded with the 4-bit vector. Fine, Manikanta. Happy? All those doubts will be cleared in the next step. Slowly we are learning. Let me complete that first basics. Then I will show you that all this. Right? So if it is 10, for example, if it is 18 is there, then what should I write? 0, 0, sorry. 0, 0, 1, 0, 0, 0, 1 and 1, 0, 0, 0. That is 18 now. 1, 8. That is not binary equivalent. Binary coded of each and every decimal digit. A code is representing one digit. That's what we need to understand. Coding, binary coded decimal. Please hold on. I will give you clarity about that. Please wait. 2-digit number, 3-digit number. How can we represent all those in BCD? I will talk. So what is it here? 8421 BCD is natural BCD, which is also called weighted BCD. Weighted BCD. What about this XS3? Non-weighted BCD. Why? The rules behind this is not weights. This representation is not using any weights. This representation is using natural BCD plus 3 is XS3. Natural BCD plus 3 is XS3 representation. XS3 representation. So one more important property we need to observe. XS3, if you are observing 0011, what is complement of 0011? 1100. 0100, complement of 0100, 1011. 0101, complement of 0101, 1010. 0110, complement of this is 1001. 0111, complement of this is 1000. Right? So what is it here? XS3 is a self-complementary. When can we say it is self-complementary? For each and every code used, complement is existing in use set only. So when we are using 4-bit combination, total 16 combinations possible. In that only 10 combinations are used for representing decimal digits. Remaining are unused combinations. So if you are observing each and every code used, complement is existing in use set only. Coming to this natural BCD, 0000 is representing 0, but 1111 is unused. Complement of 0000 is 1111. 1111 is unused. 1111 is unused. So natural BCD is weighted but not a self-complementary. Natural BCD is weighted but not a self-complementary. Once again, natural BCD is using 8421 weights. So it is called weighted BCD. It is called weighted BCD. But if you are observing complementary or self-complementary, it is not satisfying. because for each and every vector, complement is not in the use set only. So for 0, 0, 0, 0, complement is 1, 1, 1, 1. It is in unused combinations. For each and every code used, complement is existing in use set only. Then it is called self-complementary. Otherwise, it is not a self-complementary. So natural BCD, 8421 BCD is weighted BCD, but not a self-complementary. Coming to XS3. What is XS3? Non-weighted. We are not using any weights for representing. What are the rules we are using? Natural BCD plus 3 is XS3. Natural BCD plus 3 is XS3. So it is not a weighted BCD. But it is a self-complementary. Why? For each and every vector used, complement is existing in used set only or used combinations only. So natural BCD is weighted but not a self-complementary. XS3 is non-weighted, but it is self-complementary. So XS3 is non-weighted. It is a self-complementary. So coming to another BCD, if I say 84 minus 2 minus 1 BCD. Let me write one more BCD, 84 minus 2 minus 1 BCD. So 0 to 9 decimal digits using 84 minus 2 minus 1 weights. Listen carefully. So using 84 minus 2 minus 1 weights, let me represent 0 to 9 decimal digits. So 0, no doubt it is 0, 0, 0, 0. 1 I need to represent. How to get 1 using these combinations? 4 minus 2 minus 1. 4 minus 2 minus 1 is how much? 1. So it is 0, 1, 1, 1. Check it correctly. 1 is represented with 0, 1, 1, 1 because 4 minus 2 minus 1. What about 2? 4 minus 2. So 0, 1, 1, 0. Correct. What about 3? 4 minus 1 is 3. So 0, 1, 0, 1. 4 minus 1. What about 4? 0, 1, 0, 0. What about 5? 8 minus 3. So 8 minus 2 minus 1. So 1, 0, 1, 1. And what about 6? 8 minus 2, 1, 0, 1, 0. What about 7? 8 minus 1, 1, 0, 0, 1. What about 8? 1, 0, 0, 0. What about 9? 1, 1, 1, 1. 1, 1, 1, 1. So 8, 4 minus 2 minus 1 are weights. So it is weighted BCD. And if you are observing complements, yes, 0, 0, 0, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 0, 1, 0, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 0, 1, 0, 0, 1, 0, 1, 1. That means it is self-complementary. It is weighted and self-complementary. It is weighted and self-complementary. It is weighted and self-complementary. Observe correctly. 8, 4 minus 2 minus 1 weights I am using, and also it is becoming self-complementary. So how to verify whether it is self-complementary or not? Simple way. If x, a digit is represented with x3, x2, x1, x0 representation, 9's complement of x must be represented with x3 bar, x2 bar, x1 bar, x0 bar. Check it correctly. If a digit x is represented with a vector x3, x2, x1, x0, 9's complement of x must be represented with the complementary vector x3 bar, x2 bar, x1 bar, x0 bar. What do you mean by this? X is 0. 9's complement of x is 9 minus 0. It is 9. 0, 9 minus 0. 1, 9 minus 1, 8. 2, 7. 3, 6. 4, 5. So 0, 9 complements of each other. 1, 8. 2, 7, 3, 6, 4, 5 complements of each other. If a decimal digit x is represented with a vector, 9's complement of x must be represented with the complementary vector. And if you are going with the weighted BCD, if sum of weights is 9, I don't need to verify whether it is self-complementary or not. Simply, it will be a self-complementary. If sum of weights is 9, it is self-complementary. Otherwise, it will not be a self-complementary. It will not be a self-complementary. Once again, if sum of weights, if it is weighted BCD, if sum of weights is 9, then it will be a self-complementary. Otherwise, it will not be a self-complementary. Check it. 8 plus 4 minus 2 minus 1. If you are adding these two, 12 minus 3, it is 9. It is a self-complementary because sum of weights is 9. If sum of weights is 9, it is a self-complementary. It is a self-complementary. So one by one. How to verify? Either it is weighted or non-weighted. How to verify whether it is self-complementary or not is if a decimal digit x is represented with a vector, 9's complement of x should be represented with the complementary vector. Should be represented with the complementary vector. So simple way is if it is weighted BCD, if sum of weights is 9, self-complementary. Otherwise, it will not be a self-complementary. It will not be a self-complementary. So now 5421 BCD, weighted but not a self-complementary. 5421 BCD is weighted but not a self-complementary. Next, 2421 BCD, weighted and self-complementary. See, weights I'm using, sum of weights is 9, then it is self-complementary. 63 plus 1 minus 1 is also weighted and self-complementary. Weighted and self-complementary. Simple way we can check if it is weighted BCD. If it is weighted, if sum of weights is 9, then it is self-complementary. Otherwise, it is not a self-complementary. So if it is a non-weighted BCD, the way we are verifying is this. The way we are verifying is this. If it is weighted, no need to verify. If sum of weights is 9, it will be a self-complementary. Otherwise, it is not a self-complementary. It is not a self-complementary. Are you there? Right? So, once again, what is it here? Weighted, non-weighted. Self-complementary, not a self-complementary. Rules for self-complementary is x, a 9's complement of x must be represented with the complementary vector. If it is weighted BCD, sum of which is 9, then it will be a self-complementary. We don't need to verify. We don't need to verify. So these are the properties which we need to know. Now, let us see here. Whatever the conversion, what is it here? BCD to XS. Let us do that. BCD to XS3, natural BCD to XS3, right? So natural BCD 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 are represented with 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1. What is this natural BCD? Natural BCD. Sitaram, if it is non-weighted BCD, how do you add? For non-weighted BCD, I mentioned another rule. If it is weighted BCD, adding weights. If it is non-weighted BCD, I mentioned another rule. Please follow. I've been shouting multiple times. This is the rule we are following. 0, 0, 0, 1, 1. 9 minus 0, 9, 1, 1, 0, 0. Complement satisfying? If it is weighted BCD, go with sum of weights. If it is non-weighted BCD, another rule I mentioned to verify whether it is self-complementary or not. Sitaram, Kandregula Sitaram. Right? Please follow, understand correctly. Right? I have been mentioning each and every concept, each and every word. I am repeating also multiple times. Right? See, if it is weighted, sum of weights. If it is non-weighted, go with this. Right? XS3. Let me write that 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0. Let me say that variables for this B3, B2, B1, B0, natural BCD. XS3, let me use that E3, E2, E1, E0. Finding expressions for E3, E2, E1, E0 in terms of B3, B2, B1, B0. So what is E3? Sigma M of, where we have E3 is 1. E3 is 1 with respect to input combination. What we have here, 5, 6, 7, 8, 9 is a min terms. 5, 6, 7, 8, 9 are min terms. Are min terms. Correct? E3 is sigma M of 5, 6, 7, 8, 9. Not completed. Plus, don't gates off because input combinations unused are don't gates. With respect to natural BCD, valid are 0, 0, 0, 0 to 1, 0, 0, 1. 1, 0, 1, 0 to 1, 1, 1, 1 are unused, which are don't gates, which are nothing but 10, 11, 12, 13, 14, and 15. And 15. So now E2 is equals to, help me, sigma M of, where it is 1, 1, 2, 3, 4, 9. 1, 2, 3, 4, 9. Plus, don't kids of 10, 11, 12, 13, 14, and 15. And what about E1, sigma M of, what we have here? 0, 3, 4, 7, 8. Plus don't gates of 10, 11, 12, 13, 14, and 15. E naught is equals to sigma M of what we have? 0, 1, sorry, 0, 2, 4, 6, 8. Plus don't gates of 10, 11, 12, 13, 14, and 15. So complete minimization using K-map. Input variables are B3, B2, B1, B0. Output variables are E3, E2, E1, E0. Find expressions for E3, E2, E1, E0 in terms of B3, B2, B1, B0. Use 4 variable K-maps. Complete this Boolean expression, sir. No need to write any circuit for this. Simply complete expression. Why I am suggesting this is in presence of don't care, sir. These are very good K-maps. Practice minimization in presence of don't kids, suggesting you solve all these minimal expressions later, not now. So leaving it to you. I hope you can do that. If you find any difficulty, let me know. I'm there to help you. Moving to next slide. Right. Now 8, 4, minus 2, minus 1 BCD2. Let me say that XS3 BCD. 8, 4, minus 2, minus 1 BCD2, XS3 BCD. Once again, we are going to write 8, 4, minus 2, minus 1 BCD. Pratik Pramod, whichever the input combinations are invalid, those are don't cares. Already, when I discussed about don't cares itself, have considered BCD. With respect to natural BCD, it is possible to occur 0, 0, 0, 0 to 1, 0, 0, 1, 1, 1, 1, 0, 1, 0 to 1, 1, 1, 1 are never occur, which are don't cares. 10 to 15 are unused, which never occur, which are don't cares with respect to natural BCD. Pratik Pramod, it is not first time I'm mentioning about don't care here. Already I mentioned the input combination for which there is no possibility for occurrence. Those are called don't cares. With respect to natural BCD, possible to occur from 0, 0, 0, 0 to 1, 0, 0, 1. 1, 0, 1, 0 to 1, 1, 1, 1 never occurs, which are don't cares. Which are don't cares. So 8, 4 minus 2 minus 1 BCD to excess 3 BCD. So 8, 4 minus 2 minus 1 BCD. What can we write? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 0, 8, 4 minus 2 minus 1 BCD. So what we can write here? 0 is 0, 0, 0, 0. What about 1? 0, 0, 0. Sorry. What is 1 in 8, 4 minus 2 minus 1? 0, 1, 1, 1. What about 2? 4 minus 2. What about 3? 4 minus 1. What about 4? 0, 1, 0, 0. What about 5? 1, 0, 1, 1. What about 6? 1, 0, 1, 0. What about 7? 1, 0, 0, 1. What about 8? 1, 0, 0, 0. What about 9? 1, 1, 1. This is what 8, 4 minus 2 minus 1 BCD. What about excess 3 in 0 to 9? 0 in excess 3 is 0, 0, 1, 1. And what about 1 in excess 3? 0, 1, 0, 0. Please don't add 3 to this. General opinions you may be having that. So for this we are adding 3. No. Already it is mentioned rules for excess 3 is natural BCD plus 3. While writing excess 3, always rules is natural BCD plus 3. Don't add 3 to this BCD. No, it will be wrong. So now excess 3 means 1 should be represented with 0, 1, 0, 0. Natural BCD plus 3 is excess 3 representation. Don't add 3 for all the representation, all the BCDs. No. So excess 3, 1 is 0, 1, 0, 0. What about 2? 0, 1, 0, 1. What about 3? 0, 1, 1, 0. What about 4? 0, 1, 0, 0. What about 5? Sorry, I did a mistake. Right. What about 4? 0, 1, 1, 1. What about 5? 1, 0, 0, 0. What about 6? 1, 0, 0, 1. What about 7? 1, 0, 1, 0. What about 8? 1, 0, 1, 1. What about 9? 1, 1, 0. This is what excess 3 representation of 0 to 9. While converting 8, 4 minus 2 minus 1 BCD to excess 3 representation. So what can we do here? Let me use variables. Let me use variables like let me use ABCD and PQRS. PQRS. So now we need to find expression for PQRS in terms of ABCD. So P is equals, help me, sigma M of what we have here? 5, 6, 7, 8, 9 plus don't kids of 10, 11, 12, 13, 14 and 15. What about Q? Help me, sigma M of what we have here? 1, 2, 3, 4, 9. 1, 2, 3, 4, 9. Check it. Q 1, 2, 3, 4, 9 plus don't kids of same. Let me say it is the same. What about R sigma M of? Help me. 0, 3, 4, 7, 8. 0, 3, 4, 7, 8. Plus don't kids are same. And S is equals to what? Sigma M of what we are getting here? 0, 2, 4, 6, 8. Plus don't kids are same. 10 to 15. 10 to 15. Then you can minimize. Then you can minimize. Just I mentioned do because 10 to 15 don't care, I can say. This is wrong. To convey this, I've been taking this example. This is wrong. Why it is wrong? Can anyone mention in the chat box? It is wrong. Whatever we have written, expressions are wrong. Right. Reason is, listen, with the yes, Chakravarti. Don't kids are there, Manisha. Don't kids are there. Yes. Using 8, 4 minus 2 minus 1 these weights, we are calculating 0 to 9. But in K-map, do we use the positions with 8, 4 minus 2 minus 1 weights? No. So to equate decimal equivalent, we are using 8, 4 minus 2 minus 1 weights. But while using K-map, the position is not with 8, 4, minus 2, minus 1 weight. When I'm using K-map, for example, if I use A, B, C, D, the position numbers are 0, 1, 3, 2, 4, 5, 7, 6, 12, 13, 15, 14, 8, 9, 11, 10. These combinations are not with respect to 8, 4, minus 2, minus 1 BCD. The numbers we have written here 0 to 9 are with respect to 8, 4, minus 2, minus 1 weights. Right? So in the K-map, the combination numbers are not equal to decimal equivalent which is represented. So I need to use a combination number with 8421 weights. Now here decimal digit it is representing, input combination number it is representing are not same. While calculating decimal equivalent, yes, we use 84 minus 2 minus 1 weight. While calculating combination number, use 8421 weights only. The position numbers are with respect to 8421 weights. In K-map, the positional value, the combination number is not with 84 minus 2 minus 1 weight. Is with 8421 weights. Right? Now tell me what is the combination numbers. 0, 0, 0, 0 is 0. 0, 1, 1, 1, it is 7. It is not 1, it is 7. 0, 1, 1, 1. So ABCD combination 0, 1, 1 means I need to use this as a min term. If I say sigma m of 7 means here it is a min term. It is not here as 1. No, here it is min term. If it is max term, here it is max term. Because the combination number is 7. Here 0, 1, 1, 0. What is this? 6. Here it is 0, 1, 0, 1. It is 5. And 0, 1, 0, 0. It is 4. Next 1, 0, 1, 1. It is 11. It is not 5. It is 11. 1, 0, 1, 0. It is 10. And 1, 0, 0, 1. It is 9. 1, 0, 0, 0. It is 8. 1, 1, 1, 1. It is 15. I hope I did my duty correctly. Understand correctly. So decimal equivalent is representing and input combination numbers are not same because in the previous example, combination number and decimal equivalent it is representing is same because inputs is 8421 BCD. Inputs is 8421 BCD. But here the decimal equivalents it is representing with the 84 minus 2 minus 1 weights. But the combination numbers we need to calculate with the 8421 weights. Now help me. Now help me. P is equals to sigma m of, which are those 11, 10, 9, 8, 15. See here these are ones. The combination numbers are 11, 10, 9, 8, 15. That is 8, 9, 10, 11, 15. Which are don't guess the combinations which are missing in red. Can you guess which are those? 1, 2, 3 missing. 12, 13, 14 are missing. 1, 2, 3 missing. 12, 13, 14 are missing. 1, 2, 3, 12, 13, 14 are don't guess. Any doubt in that? No doubt. Because the combinations which are not possible to occur are don't cares. In this red, if you are observing 1, 2, 3 are missing, 12, 13, 14 also missing. Then Q is equals to, help me, sigma m of what we have here 7, 6, 5, 4, 15. That is the 4, 5, 6, 7, 15. Plus don't cares are same. 1, 2, 3, 12, 13, 14. R is equals to sigma m of what we get here 0. Next 4, 5. Next 8, 9. Check it correctly. I'm using red numbers which are in red, which are input combination numbers, which are don't care. Yes, 1, 2, 3, 12, 13, 14. Now S is equals to sigma m of what we are getting here 0, 6, 4, 10, 8. That means 0, 4, 6, 8, 10. Plus don't get same. You can use these numbers correctly. Otherwise, answer will be wrong. So sometimes it may be asked only one expression in the options. Once it is given, this type of questions. When you are converting ABCD 84 minus 2 minus 1 BCD to XS3 PQRS, if I use variables, the expression for P, they are giving options. Don't think that these type of questions will not be given in objective exam. Yes, it will be given. It can be given. Already once it is given, I can frame n number of questions based on this also. But we should know concept. If you are understanding concept, it is possible to answer any question. Right? Any question. So the numbers which we are considering are with respect to weighted BCD or weights, or you are using input combination numbers. What is that correct? We need to observe. So while equating numbers, I should go with the weight specified. While using K-map, you should go with the input combination numbers. Input combination number is different if it is a weighted BCD, if you are using other than 8421 weights. If you are representing BCD using other than 8421, you need to check that input combination numbers is different. Decimal equivalent it is representing is different. Follow correctly. Yes. Right. Yes. Whichever combinations are missing in input combination numbers, not the numbers in decimal. Always decimal will be 10 to 15 only. Right? No. Whichever the numbers are missing in input combination numbers, those are unused combinations. Those are don't care combinations. With respect to input combination numbers with 8421 weights. So Param, what is the don't care I mentioned while discussing? The input combinations for which there is no possibility for occurrence are called don't cares. The input combination for which there is no possibility for occurrence are called don't cares. In this input combination which are not possible to occur, in this red which are missing, 1, 2, 3 is there. Check it that 1, 2, 3 are missing. Again 12, 13, 14 are missing. The numbers which are missing should be considered as don't cares in input combination numbers. The input combination which are not possible to occur are considered as a don't cares, which never occur. The input combination which never occur, clearly I have been mentioning from day I started about don't care. Param, Mr. Param. Same thing I explained. Listen, Param. Here, input combination numbers is same and decimal equivalent is representing is same because it is 8421 BCD. Input combinations also calculated with the 8421 only. So decimal equivalent it is representing is also calculated with the 8421 because natural BCD 8421 BCD. Param, I explained the same. I know you will get this doubt. That is the reason by going back to this slide I mentioned. In this input combination numbers is same, decimal equivalent it is representing is same because 8421 BCD. So while calculating decimal equivalent, we are using 8421. While calculating input combination numbers, we are using 8421. But here, while calculating decimal equivalent, we are using 84 minus 2 minus 1 weights. While calculating input combination numbers, we are using 8421. When weights are different, we are getting different numbers, right? But What should I do? By equating these, I should go with the decimal equivalent. While using K-map, I need to go with the input combination numbers. While calculating input combination numbers, 0, 0, 0, 0 is 0, 0, 1, 1, 1, using 8421 weights, if you are calculating 0, 1, 1, 1 is 7, 0, 1, 1, 0 is 6, 0, 1, 0, 1 is 5, 0, 1, 0, 0 is 4. So we are calculating input combination numbers. Whichever the combinations are missing in this input combination numbers, for those, there is no possibility for occurrence. That is the reason the combination which are missing are called don't cares. Param, param. Yes, param. Please don't deviate from the class. Give your 100% presence. I'm there to help you. If I keep on repeating for one, right, I need to repeat for 100 plus times. So please focus on my words, sir. I've been repeating. I know what type of doubts students will get because a little bit experience I have in teaching, right? Param, you haven't replied. Have you understood now? Don't care. Yes, thank you. If you're understanding, if you're accepting for me, I'm not there to help you. Again, even though you're not understanding, if you say yes, I'm not responsible. If you're not understanding, you can mention that, or you can wait for question hour. We discuss. We discuss if you are not understanding, right? Okay. Okay. What is Anand Barud? What you're asking? 8, 4 minus 2 minus 1 weight. I'm not writing here directly. I have already discussed here. Please. Already discussed how we are representing 8, 4 minus 2 minus 1 BC. Again, you are asking that explain 8, 4 minus 2 minus 1 BCD once again means, what should I do? So individually, I need to take tuition. Please understand. See, already I have discussed 8, 4 minus 2 minus 1 BCD. Shesha Surya Sai. What is that you are expecting? In this, simply I'm writing first 8, 4 minus 2 minus 1 BCD combinations. 0 to 9, how I'm representing using 8, 4 minus 2 minus 1 weights. These are the combinations. What is XS3? Natural BCD plus 3 is XS3. So I know these. See, already in this, this is XS3, right? This is XS3. This is what 8, 4 minus 2 minus 1 BCD. So I'm writing these as input, these are outputs, equivalents. So I'm writing, see, in this, what I've written, this is 8, 4 minus 2 minus 1 BCD as inputs and XS3 as outputs. And after that, what we are doing, these are with different weights. So I cannot use these as input combination numbers because while calculating decimal equivalent, I'm using 8, 4 minus 2 minus 1 weights. It is already done here. How I'm representing 0 to 9 using 8, 4 minus 2 minus 1 weights. Please understand. I'm not assuming you should know this basics. I'm not at all assuming. I've been explaining everything. So what is that input side here? 8, 4 minus 2 minus 1 BC. What is that output side? XS3. I'm equating because 0 to 9 representation is this. But while using K-map, I cannot go with this 0 to 9 numbers because these 0 to 9 numbers are calculated here with 8, 4 minus 2 minus 1 weights. But while using K-map, I need to calculate the numbers with 8, 4, 2, 1 weights. But what is that here? We have used 8, 4 minus 2 minus 1. But using 8, 4, 2, 1 weights, if you're calculating input combination numbers, the numbers we are getting in red. The numbers which are in red are input combination numbers. So with respect to these, I need to write output expressions in terms of input variables. So here P is 1 for input combination numbers. Don't use that 5, 6, 7, 8 now. What is it here? Here it is 1, here it is 1. All these are ones. Which are those? 11, 10, 9, 8, 15. That's what I have written here. Order 8, 9, 10, 11, 15. And what about don't cares? The numbers which are missing in input combination numbers are don't cares. Which are those? 1, 2, 3 missing, 12, 13, 14 are missing. So don't cares of 1, 2, 3, 12, 13, 14. Similarly, I have completed remaining also. Shesha Surya Sai. Understood now? So can you please go to carry look at Lal Krishna? We are in this. You are asking that go to carry look at right? Right? So Vamshi Krishna, you are doing a mistake. Just check it. You are doing a mistake. To get it equal, what should be there? Exactly, it must be same. 0, 0, 0, 0, 0, 0, 0, 0. 0, 1, 1, 1, 0, 1, 1. Then we are getting that same. You are doing a mistake. Vamshi Krishna, go with the K map correctly. One more important concept in this BCDs I am addressing. Listen. Right. Yes. 0 to 9, natural BCD I am talking. 0 to 9 are represented with 0, 0, 0, 0 to 1, 0, 0, 1. For example, if you have a 86.03, if I say this is a decimal number, how to represent in BCD? 8 is represented with 1, 0, 0, 0. Natural BCD I am writing. 6 is what? 0, 1, 1, 0. Point 0 is what? 0, 0, 0, 0. What about this 3? 0, 0, 1, 1. Simply replacing digit by digit with code. That is called coding, binary coding. It is not a binary equivalent. Binary equivalent is nothing but divisions of integer part, multiplication, fraction part we can do. But when we are coming to BCD is nothing but coding each and every decimal digit with binary vector, binary vector. So each and every decimal digit is coded with 4-bit vector. If I say natural BCD, this is 86.03 this is the representation in BCD. Each and every digit is coded with a 4-bit vector. 4-bit vector. Right. While representing one-digit BCD, that means 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 are represented with 0, 0, 0, 0 to 1, 0, 0, 1. 1, 0, 0, 1. So in this 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. How many combinations? 6 combinations are unused. What is it here? Unused combinations. How many? 6 combinations. In representing one-digit BCD, 6 combinations are unused. Be clear. Once again, what is it here? In representing one-digit BCD, we are getting that the 6 combinations are unused. In representing 2-digit BCD, how many combinations are unused? Take time once again. In representing one-digit BCD, the unused combinations are how many? 6. Because 4-bit vectors we are using, in that 0, 0, 0, 0 to 1, 0, 0, 1 are valid, are used. Then 1, 0, 1, 0 to 1, 1, 1, 1 are unused combinations. How many combinations are unused? 6 combinations are unused. When I'm when I'm representing 2-digit BCD, how many combinations are unused? When I am representing 2-digit BCD, how many combinations are unused? Please check, take time and answer this question. Ananda, just now I mentioned how I am writing the 2 digits in BCD. Now you are asking how 2 digit is, how it can be BCD means. Each digit is represented using 4-bit vector. When I have the 2-digit decimal number, how can I represent in BCD? Just now I mentioned. Then again you are asking that it is 2-bit I mentioned. No, it is 2-digit I mentioned. Anand, understand question correctly. Just now I have shown how we are representing if we are having more number of digits. Till now I did not get a correct answer. Yes, I got one correct answer till now. Very good. Very good. Yeah, Sampath Kumar, you are near to the answer. Somewhere you are doing a mistake. Now, let us see. I can use a logic. Simple logic I can use. Listen. When I'm using 2-digit BCD means how many vectors, how many binary bits I use? To represent 2-digit BCD, how many bits I use? 8 bits. How many bits I'm using to represent 2-digit BCD? 8 bits. Any doubt in that? 1 bit, 1 digit 4 bit, 2 digit 8 bits. Then how many, just a minute. How many input combinations possible when I'm using 8 bits? 2 power 8 combinations, am I right? How many combinations are possible? 2 power 8 combinations are possible. Right? When I'm using 8 bits, 2 power 8 combinations possible. In these, how many are valid in 2-digit decimal number? I have 0, 0 to 99. How many are valid? 100, right? Simple thing. Total combinations possible is 2 power 8. Why? I'm using 8 bits. Why? 2-digit BCD means 1 digit is 4 bit, another digit is 4 bit. Total 8 bits I'm using. When I'm using 8 bits, 2 power 8 combinations possible total. In that, valid combinations is how many? 0, 0 to 99. When I'm using 2 digits, what is the possible number in decimal? 0, 0 to 99. Decimal number valid is 0, 9 only, 0 to 9 only. So 0, 0 to 99 are valid means 100 combinations are valid. So total combinations minus valid combinations is giving 156 invalid combinations. Check it. 2 power 8 is 256. 256 minus 100. Simple thing. Simple logic. See, when I'm using 2-digit BCD, to represent each digit, I'm using 4 bits. 2 digits means total 8 bits. Total number of combinations possible is 2 power 8. In that, valid combinations we can say easily. How? Decimal numbers using 2 digits means it can be 0, 0 to 99. Right? 0, 0 to 99. How many can be there? 100 combinations are valid. When 100 combinations are valid, remaining are invalid. Check it. Logically, we can proceed. It is a 156. Now tell me, how many combinations are invalid in representing 3-digit BCD? How many combinations are invalid in representing 3-digit BCD? Now you should say correctly. Right. In 3-digit BCD, how many combinations are invalid? Ashutosh, you did a mistake. Check it. Typing error or something else. Check it. Toyajakshudu, correct. Nagalingeshwara, correct. Yes. Gurudatta, check your answer. Deepa, please check your answer. Manisha, you are right. Who is that? Not Gurudatta. Again, you are wrong, I think. Check it. Excellent. Once we are giving concepts, yes, invalid combination I'm asking. Sai Kumar, invalid. Do you say that question is invalid? Satvik Behra, you are doing a mistake. Pavan Kumar, you did a mistake. Valdika, did a mistake. Manikanta, did a mistake. Manikanta Choni, you did a mistake. Yes, Sai Kumar, it is correct. KVM Sai Kumar. Invalid combinations is the number is correct. Deepa, who is that? The big number. I'm not able to. Vamshi Krishna. What is that number, Nana? Okay, not Vamshi Krishna. Annapurni. Why are you getting that number? Rajita Basiti. Why are you getting that number? Right. Now, let me give my answer. Most of you have answered correctly. When I am using 3-digit BCD, how many bits I will have? Each digit 4 bit. 3-digit 12 bits. 3 4 12. Am I right? To represent a 3-digit BCD, 3-digit BCD is equals to 12 bits. Am I right? 12 bits, na? 1 digit is 4 bits, 3 digit is 12 bits. When I am using 12 bits, total number of combinations possible is 2 power 12. Be clear. When I am using 12 bits, why it is 12 bits? As I am using 4 bits for representing 1 digit. When I'm saying that 3 digit, 3 4s are 12 bits I need to use for BCD. So when I'm using 12 bits, total number of combinations possible is 2 power 12. In that, how many are valid? 0 0 0 to 999. How many can be there? 1000. Check it. 0 0 0 to 999. That is 1000. So that is 1000. Then 4096 minus 1000 is equals to 3096. Now, n digit. Let me go for n digit. N digit means 4n bits. Check it correctly. Each bit is 4 bit. N digit is 4n bits. Total number of combinations possible is 2 power 4n minus how many are valid? 10 power n. 1 digit 0 to 9, 10, 10 power 1. 2 digit 0 0 to 99, 10 power 200. 3 digit 10 power 3, 1000. 4 digit 10 power 4. Right. It is n digit 10 power n. मजा आ रहा है? Some competitive exams they have asked twice or thrice these type of questions, invalid combinations. When we know total minus valid, we can say invalid combinations. Invalid combinations. Okay, Annapurni, not a problem. Very good, Toyajakshudu. Good way of analyzing, right? Badana. Okay, thank you, Ashutosha, if you're appreciating about the question. Okay, now from today, bit extension may be there in the class. If there is no any disturbances, be ready for that because it's taking more and more time because it is an online platform, right? So be ready for that. Little bit extension. How much time depends on my patience and your interest. If you are interested, I will continue till 8 or 9 also, not a problem for me because we are habituated to take the classes from morning 6:30 to evening 8:30. But nowadays, I think we are losing that enthusiasm because it was offline, now it is online, right? Okay. Now, we'll see. Right. Now, some people were asking about some questions. Let me answer those questions. Uh, f of v comma w comma x comma y comma z is equals to x plus y bar z. The number of minterms excluding redundant terms. This was a question in Boolean algebra logic gates. Some people were reminding me about this question. That is the reason I'm answering this question. F of v comma w comma x comma y comma z is equals to x plus y bar z. X plus y bar z. Now I need to calculate a total number of minterms in this function, excluding redundant terms. Excluding redundant terms. Okay, Ankur. Okay, Ankur. Okay, I will discuss, right? Okay. So how many variable function is that? 5 variable function, right? According to the concept, m variable k map grouping to power n number of adjacent cubes eliminating n variables, resultant term is of m minus n variables. We will discuss point m variable k map grouping to power n number of adjacent cubes eliminating n variables, resultant term is of m minus n variables. Am I right? So resultant is of one variable. How many variables are eliminated? 4 variables because function is of 5 variables. Listen, conceptually we are going to understand. So 5 variable function, resultant term is of one variable. That means how many variables are eliminated? 4 variables. 4 variables can be eliminated when we are grouping to power 4 number of adjacent cubes, which are minterms. Any doubt in that? 4 variables are eliminated. 4 variables can be eliminated when we are grouping to power 4 number of adjacent cubes which are minterms. Am I right? See, 5 variable function, resultant term is of one variable. Then how many variables are eliminated? 4 variables. 4 variables can be eliminated when we are grouping to power 4 number of adjacent cubes. Plus y bar z. How many variables are there? 2 variables are there. How many variables are eliminated? 3 variables are eliminated. When is it possible? When we are grouping to power 3 number of adjacent cubes. How much is that? 16 plus 8, which is 24. Which is 24. Which is 24. Is wrong. It is wrong. Why? There are common minterms in these two. Those are counted twice. Check it correctly. There are common minterms in these two groupings. That common minterms are counted twice if you are calculating separately. So the common is counted twice. Only once it must be counted. Once it must be deducted. Point should be understood correctly. If you're calculating like this, no doubt there may be common minterms. The common minterms are counted twice. That is not eliminating redundancy. That extra must be excluded. That extra, the common is counted twice. It must be counted only once. That extra, which is redundant, must be excluded. How is it possible? If you remember the formula, N of A union B is equals to N of A, counting N of B minus N of A intersection B. Right? Now, one by one. N of A means X minterms. N of B means Y bar Z minterm. N of A intersection B. How to get intersection? How to get intersection? Minterms intersection. ANDing. If you remember, when you're ANDing two functions, we are getting intersection. Right? So, if you're ANDing these two, what we get? X, Y bar, Z. Logical. Yes. So, intersection is nothing but common minterms. Common minterms. How to get common minterms? By ANDing. Already we discussed this concept. So now I can count. X minterms is 2 power 4. Y bar Z minterms is 2 power 3 minus XY bar Z minterms is how many? 2 power 2. Why? Now it is 3 variables. 2 variables are eliminated. It is possible with 2 power 2 only. Right? 16 plus 8 minus 4, which is 20. Answer for this question is 20. Why? X, Y bar, Z is common term or intersection term. So for that, how many minterms will be there? 2 power 2. Why? 3 variables are there in that. 2 variables are eliminated. 2 variables can be eliminated with 2 power 2 adjacent cubes. Right? Answer is 20. Answer is 20. Understanding? For this, we can write K map also. We can understand with the K map also. How 2 to the power 2? Right? Yes. Here, in this intersection means ANDing these two. We are ANDing intersection. So when you're ANDing these two, what we are getting here? X, Y bar Z. X, Y bar Z means how many variables are there? 3 variables are there. How many variable function is that? 5 variable. How many variables are eliminated? 2 variables. When is it possible? 2 power 2 number of addition. Two minutes. Ah. Just recharge with a cup of tea. Right. Okay. So I have been trying to build the basics from day one. See, the concepts, if you are observing, I have discussed these concepts long back. How to get intersection using Venn diagrams as well as functions F1, F2. By using F1, F2, I have discussed what is intersection, how to get intersection, how to get union, what is R function, what is AND function, what is inversion. All these already discussed. And K-map minimization principle, there I mentioned how many cubes we are grouping, how many variables are eliminated, how many variables will be there in the resultant. The concept I've been mentioning, right? So that's the reason I say from day one, don't miss the classes, follow correctly, utilize the concepts, will help you in understanding next level of questions in less time. You may be getting answer, but you should get answer in less time. Even for this also, I have very big explanation. It will take around 10 plus minutes or 20 minutes around for this. Simple thing is how to proceed. Total minus valid is becoming invalid. Otherwise, writing a digit, or it may be valid, it may be invalid, and so and so. So here also, we can use another method also. What is the other method? Let me show you that. What I can do here is writing K-map. Understand correctly? Writing K-map. What is that K-map? 5 variable K-map, right? Are you understanding? 2 K-maps? One for V equal to 0, other one is for V equals to 1. Because VW XYZ. So now here I can write W X Y Z 0 0 0 1 1 1 1 0. Common for both the K-map 0 0 0 1 1 1 1 0. Can you say what is the first term? X. What do you mean by X? See, X equals to 1, all the variables are changing. Or let me use the other thing. This is a grouping, right? In which, right, V equal to 0 is included, V equals to 1 is included. Then all these are minterms. Let me write those minterms. All these are minterms. Next, what is second one? Y bar Z. Second term is Y bar Z. What is it? Y bar Z? This is the Y bar. This is Y bar Z, right? So here all these are minterms. Now you can count the number of minterms. In this 16 plus 2 plus 2. That's it. But if you are counting separately, what happened here is this 4 is common for these two. The 4 was counting in X, 4 was counting in Y bar Z. That is the reason 4 was extra. Actually, it is 20 only. But this 4 was counted in X, this 4 was counted in Y bar Z also. Maza aa raha hai? See, Nagalingeshwar Rao, very good doubter. For example, if you are having two terms like this, X, Y bar and Y bar Z, YZ is there. For example, XYZ, in WXYZ, we have that XY bar and YZ is there. Then what will be the intersection? We are ending these to 0. Nagalingeshwar Rao, I hope I am addressing your doubt. XY bar is another one term, YZ is another term. Then when you are adding these two are mutually exclusive. There won't be common min terms. There won't be common min terms. Yes, sir. N of A plus N of B plus N of C plus minus N of A intersection B minus N of B intersection C minus N of A intersection C plus N of A intersection B intersection C. Sivalila. I hope you know that N of A union B union C. N of A plus N of B plus N of C minus N of A intersection B minus N of B intersection C minus N of A intersection C plus N of A intersection B intersection C. Sivalila. Nagalingeshwar Rao, I hope you understood, right? Correct. When you are adding two terms, if it is resulting 0, there won't be any intersection. Common min terms are not there. Those two groupings are mutually exclusive. Then there won't be any common min terms. Then intersection becomes 0. That's it. Right. Search for the formula, Chakrabarti. A, B, C, D. Search for the formula. A union, B union, C union, D. Right? You search for the formula. Chakrabarti. Set theory. Can you mention that, Kashyap, what is that question? Question number 4. Is it a maximum number of prime implicants? From KMAP, fourth question, if you are saying that, is it a maximum number of prime implicants? Is that? Yes. I'm going to answer that question only. Again, an ambiguous question, right? Let us see. We have a controversy with that question. I'll show you that. Right. So maximum number of prime implicants of n variable function. That is the question. Actually, answer is given to power n minus 1. To power n minus 1. Manikanta, I will answer your doubts, sir. Please wait. Right. Shivalila, go with the K-map. Better to express the K-map, right? In the K-map, right? They won't give you more than 4 or 5 variables. So 5 variables is a very difficult question. There may not be, right, more than that variables. Just go through that. Right. So I'm answering question from K-map. Many have been, right, requesting for that question. There is nothing but maximum number of prime implicants possible for an n variable function. Is question correct? Right. Saidama, I will discuss all the questions, not only question number 3 or question number 2 or question number 1. So as many were facing this problem, as people were messaging me on WhatsApp about this question, I'm answering. Let me answer that question. So afterwards, by putting all these questions in the slides, I will answer the questions. Don't need to worry. So if you are facing any problem, I'm there to help you. Right? So the question is the maximum number of prime implicants possible for n variable function. Actually, it is not prime implicants. It is essential prime implicants. It is essential prime implicants. See how it is essential prime implicant. Why can't it be prime implicant? I'll say that. So if I take a 3 variable function, if I take a 3-variable function, example 3-variable function, A, B, C, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. If I say this is a function, how many prime implicants are essential? 1 grouping, 2 grouping, 3 grouping, 4 grouping. 4 are essential. Any doubt in that? These 4 are essential. Any doubt in that? In this, we have 4 essential prime implicants. If I take a 4-variable K-map, for example, 4-variable K-map. If I consider K-map like this. Right? How many are essential? 1, 2, 3, 4, 5, 6, 7, 8. All these are essential. So not only this, for this, we can have another K-map also, which is having 4 essentials. What is it here? It is like this. N input XOR and XNOR cannot be minimized further. All those terms are essential. N input XOR and XNOR. So here it is XOR, here it is XNOR. Here it is a XNOR. We can have remaining also min terms, that is a XOR. Then what is it here? N input XOR and XNOR cannot be minimized further. All those terms are essential. All those terms are essential. When we are considering 3-variable, we are using 4. We are getting 4. When we are using 4-variable K-map, we are getting 8. When we are using n-variable, to power n minus 1 number of essential prime. The maximum number of essential prime implicants can be 2 power n minus 1. 2 power n minus 1. Check it correctly. 2 power n minus 1 maximum essentials. If you're adding any term, it may be changing number of prime implicants, but the essential prime implicants may be reducing, but it cannot be increased. If I'm adding anywhere in these min terms, it may be changing number of prime implicants, but number of essential prime implicants can be reduced but cannot be increased. Right? So answer is 2 power n minus 1. N input XOR and XNOR cannot be minimized further. Cannot be minimized further. So in that XOR or XNOR, when we have that n variable 2 power n combinations, half of the combination it is 1, half of the combination is 0. Then maximum number of essential prime implicants can be 2 power n minus 1. Then you may be having it out. Why can't it be prime implicants? Yes, I will give you clarity about that also. Why can't it be prime implicants? I can take an example. Find number of prime implicants, number of essential prime implicants, and minimal expression. Find number of prime implicants, number of essential prime implicants, and minimal expression. So if you are grouping for prime implicant 1, 2, 3, 4, 5, and 6. How many prime implicants? 6. The essential prime implicants is 0. Right? So if the question is with prime implicants, 2 power n minus 1 is wrong. Because it must have only 4 prime implicants. No. 4 essential prime implicants is maximum accepted. Prime implicants can be more than that. So the 2 power n minus 1 is essential prime implicants. Question is wrong, which is printed wrongly. So it is essential prime implicants. Now, what is the minimal expression of this? See, what is the minimal expression of this? Now, what I consider here, this is one grouping. Now I need to choose non-essential. These three I can choose in the minimal expression. Then what I get? B bar C bar plus AC, correct? Plus A bar B. This is B bar C bar. This is A C. This is A bar B. Now, similarly, what we have here, I can choose this plus this plus this. And what we get here, it is A bar C bar plus A B bar plus here it is BC. These two are having same complexity. Once again, we are getting two minimal expressions. Check it correctly. Either we can use a set which is in blue or we can use the set which is in green. All these two sets have been covering all the minterms with minimum complexity only. So finally, we are getting two minimal expressions, but prime implicants were 6. So the essential prime implicants cannot exceed 4. It can be less than that. Maximum means it can be less than that. But maximum, these are the possibilities for getting essential prime implicants. Yes or no? Each and every concept, right? PI equals to EPI, so is true. Where? In this? No. Clear? Very good. Okay. Right. Now, one more. When we have n variables, how many maximum number of functions possible? Listen carefully. How many maximum number of functions possible? When we have n variables, how many maximum number of functions possible? See, if I say two variables, listen, if I say two variables, so now function 0, 0, 0, 1, 1, 0, 1, 1 combination. How many combinations possible? 4 combinations. Now, the function can be defined either 0 or 1. So, it can be like this 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, so and so 1, 1, 1, 1. How many functions possible? How many functions possible? 2 power 4 functions possible. Am I right? Understand correctly? When I'm using two variables, simple two variable function, two variables means 2 power 2 4 combinations possible. Each and every combination, you can define either 0 or 1. The possibilities, if you are observing 0, 0, 0, 0, 0, 0, 0, 1, so and so, 1, 1, 1, 1. How many? 16, which is nothing but 2 power 4. What is 4? Number of combinations possible. So, if it is 3 variable, for example, if I say 3 variables, A, B, C, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. The function can be now 0, 0, 0, 0, 0, 0, 0, 0, 0, 2, 1, 1, 1, 1, 1, 1, 1, 1. How many? 2 power 8 functions. How many? 2 power 8 functions. For 3 variable, 8 combinations possible. For 3 variable, 8 combinations possible. How many functions? 2 power 8. For 2 variables, 4 combinations possible. Functions 2 power 4. For n variables, how many combinations possible for n variables? 2 power n combinations possible. How many functions possible? 2 power n. See, I can write 2 power 2. I can write 2 power 3. What is this number of combinations? What is total number of functions? What is this 2 power 2? Number of combinations. What is 2? Number of variables. What is 2 power 2? Number of combinations. What is 2 power 2? Number of functions. What is n? Number of variables. What is 2 power n? Number of combinations. What is 2 power n? number of functions. Number of functions. Am I right? So maximum number of functions possible of n variable is 2 power n. 2 power n. Right? Check it correctly once again. When we are having two variables, total number of combinations possible is 4. Total number of functions is 2 power 4. When we are having three variables, total number of combinations possible is 2 power 3, which is 8. So number of functions is 2 power 8. When we are using n variables, total number of combinations is 2 power n. Total number of functions is 2 power n. 2 power n. Right? 2 power n. Why did you get doubt, Gummuluri Pavan Kumar? Are you not able to write that functions which you are expecting with one variable? Confidence, I can see, right? A, one variable. Pavan is having a doubt about one variable. So I can have a 0 or 1, two possibilities, right? Now function can be 0, 0, 0, 1, 1, 0, 1, 1. How many functions possible? How many functions possible? 4 functions. 2 power 1. It is 4. Pavan. Gummuluri Pavan Kumar. You thought it will be wrong with one variable, right? Please respond if you are understanding. Yes, if you are understanding, thank you. Yes, one more thing. One more important thing I'm addressing. Please focus on this, right? So if you are having any doubt, we discuss after this concept, right? Maximum number of n variable self-dual functions, right? Maximum number of n variable self-dual functions. Maximum number of n variable self-dual functions. That's what I need to calculate, right? If I go with the two variable functions, f of a comma b, is it self-dual or not? Yes, answer is that Nagalingeshwara. But some of your friends may not be knowing the concept. Let me give the concept also instead of giving answer only. Yes, whatever you said, answer is correct. But if I give only answer, do you accept? Some of your any problem? Anusha, Ajay, Prithviraj, I will answer your questions later. Let me complete this concept. Anusha. Right. So f of a comma b is equals to a. What is dual of this? What is dual of this? A itself. Any doubt in that? We are getting A itself. F of A comma B is equals to A bar. What is dual of this? Same. While writing dual, we are not complementing. Right? F of A comma B is equals to B is also self-dual. F of A comma B is equals to B bar is also self-dual. For example, if I take F of A comma B comma C is equals to AB plus BC plus AC, also self-dual, let us verify. If you write dual of this, I am writing dual of this. Please help me in writing that. Dual of this F of A comma B comma C, FD, A plus B, right? B plus C and A plus C, right? A plus B and B plus C and A plus C. Now, when you are adding these two, what we get here? AB plus B, I'm adding these two. And again, AC plus BC and with A plus C. Check it correctly. AB and with A, AB, B and with A, AB, AC and with A, AC, BC and with A, ABC plus ending with this again ABC plus here B and C, BC, AC and with C, AC, BC and with C, BC. So AB plus AB is AB, right? BC plus BC is BC, AC plus AC is AC plus ABC plus ABC. ABC plus ABC is ABC. So if I take a AB, right, plus BC, in these two, if I take AC common, one logical RB. One logical RB is one. So AC and with one is AC. So AB plus BC plus AC is also self-dual, right? Is also self-dual. Am I right? So AB plus BC plus AC is also self-dual. So after understanding this, F of A comma B equals to A means what is it? Canonical AB bar plus AB is equals to sigma M of what is it here? Combinations 1 0 1 1. Am I right? Sigma M of 2 and 3. Check it correctly. Sigma M of 2 and 3. Now coming to this one. A bar means what? A bar B bar plus A bar B. So A bar B bar means 0 0. A bar B means 0 1. So sigma M of 0 1. And what about B? A bar B plus AB. A bar B plus AB means 0 1 and 1 1. Sigma M of 1 and 3. B bar means A bar B bar plus A B bar. Canonical 0 0 1 0. Sigma M of 0 and 2. Right? So what can we write here? Please help me. AB means C is missing 1 1 0 1 1 1. Correct? BC means A is missing 0 1 1 1 1 1. Am I right? Now AC means B is missing 1 0 1 1 1 1. Right, canonical is equals to sigma M of what we have here 3 5 6 7. 3 5 6 7. Right. After this, you can understand one important thing. See, 2 is minterm means 1 0. 3 is minterm 1 1. 0 is minterm 0 0. 1 is minterm 0 1. So 1 is minterm 0 1. 3 is minterm 1 1. 0 is minterm 0 0. 2 is minterm 1 0. See, if 0 0 is minterm, 1 1 will not be minterm. If 0 1 is minterm, 1 0 is not minterm. If 1 0 is minterm, 0 1 is not minterm. If 1 1 is minterm, 0 0 is not. What do you mean by this, sir? 0 0 1 1 are reciprocal to each other. 0 1 and 1 0 are reciprocals to each other. Complementary vectors. If you are observing this 1 0 1 1, 1 0 is from this set, 1 1 from this set. 0 0 is from this set, 0 1 is from this set. So 0 1 is from this set, 1 1 is from this set. 0 0 is from this set, 1 0 is from this set. What do you mean by this? It is forming a function choosing one minterm from each set. Right? Don't worry. Hold on. Take time. So what is 3? 0, 1, 1. What is 5? 1, 0, 1. What is 6? 1, 1, 0. What is 7? 1, 1, 1. See, 0, 1, 1. Reciprocal is what? 1, 0, 0. Is it there as a minterm? No. 5, 1, 0, 1 is a minterm. What is reciprocal? 0, 1, 0. Is it a minterm of this? No. Right. Next, 6, 1, 1, 0 is minterm of this. What is reciprocal? 0, 0, 1 is not a minterm. 7, 1, 1, 1 is a minterm. 0, 0, 0 is not a minterm. That means these two are set, these two are set, these two are set, these two are set. Right? Now, understand this correctly what is happening. 0 and 3 are one set, 1 and 2 are another set. In this, if you are observing three variables, just write it. What is here? 0, 7, one set, 1 and 6, one set, 2 and 5 is another set, 3 and 4 are another set. So finally, what is it here? When we are writing, wait, don't raise the hands, please, hold on. With respect to two variables, I'm talking. 0 and 3 are one set because these two are reciprocal. 0, 0, 1, 1. And 1 and 2 means 0, 1 and 1, 0 are another set. So I can choose one from this to form a self-dual function. I can choose one from this. That means I can choose 2C1 ways one from this, 2C1 ways another one from this. 2 into 2, total 4 functions possible. 4 functions possible, self-dual. Coming to three variables, 0 and 7. Check it correctly. 1 and 6, 2 and 5, 3 and 4. From each set, I have to choose one. That means from this one, 2C1 way. From this 2C1 way. From this one, 2C1 way. From this 2C1 way. 2 into 2 into 2 into 2. How many? 2 power 4. For three variables, 16 self-dual functions are possible. When we are coming to n variable, help me. 0, 2 power n minus 1. 1, 2 power n minus 2. So and so, 2 power n minus 1, 2 power n minus 1. Check it. I have to choose one from this. What is it here? 2C1, 2C1, so and so, 2C1. So 2 into 2 into 2, how many times it is there? How many combinations for n variables? 2 power n combinations. How many pairs will be there? By 2. It is a 2 power n minus 1 pairs. So 2 power n minus 1 times means 2 power n minus 1. These are self-dual functions. These are self-dual functions. Some of you may be in a bit confusion expected, but answer is this 2 power n minus 1. But concept is this. Observing self-dual functions. If an input combination is minterm, reciprocal combination should not be a minterm. Right? So two conditions should be satisfied. Listen, two conditions. If I have a X number of combinations, half of the combinations must be there as minterms. Every self-dual function is having half of the combination as minterm. In that, if an input combination is a minterm, complementary vector should not be a minterm. That means what I'm doing here is I'm making sets combination complementary vector 0, 0, 0, 1, 1, 1. So I can choose one from this and 0, 0, 1, 1, 1, 0. What is that here? 0, 0, 1 complement is 1, 1, 0. I can choose only one from this. Which one? No priority, but I can choose only one from this. 0, 1, 0 complementary is 1, 0, 1. 0, 1, 1 complement is 1, 0, 0. That means these are reciprocal combination set. I have to consider 4 minterms, one from each set. So selecting one from each set is 2C1, 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 2C1. So total 2 power 4, 16 functions. Coming to n variable, observe correctly. Coming to n variables means 2 power n combinations. I'm making pairs. How many can be there? pairs, if I say k pair, number of pairs, 2 power n minus 1. Because in each pair we have two combinations. So total combination is 2 power n, and half of that is 2 power n minus 1. 2 power n minus 1. Check it correctly. N variable 2 power n combinations. N variable 2 power n combinations. Then number of sets, half of that. 2 power n by 2, it is 2 power n minus 1. So that is the reason 1 from each pair. How many pairs? 2 power n minus 1 pairs. So 2 is multiplied for k number of times. K is what? 2 power n minus 1. Simple thing. So 2 power n minus 1. 2 power n minus 1. So that is a maximum number of self-dual functions. Maximum number of self-dual functions. If you are not able to catch the concept, just remember this answer. They may be asking for n variable, they may be asking for 3 variables, they may be asking some x number of variables. So you must be in a position to answer this question. So in objective, they may not be asking you to prove, but by knowing concept, it will be helpful. That is the reason I explained. So one thing is when you have some number of combinations, when you are using n variables, 2 power n number of combinations possible. Half of the combination must be considered as minterms of self-dual function. And second condition is if an input combination is a minterm, the reciprocal combination should not be a minterm. That is the reason mutually exclusive combinations we are making sets. From each set I can choose one. Which one is that? No priority. That is the reason equal combinations. Selecting one from this set, 2C1 ways, selecting one from this set, 2C1 ways, selecting one from this 2C1 ways, selecting one from this set, 2C1 ways. So 2 into 2 into 2 into it is 2 power 4, it is 16. Right? So like that, when you are having 2 power n combinations, 2 power n minus 1 pairs are possible. So from each pair, one can be selected, 2C1, 2C1, so and so, 2C1. Then, so how many pairs? 2 power n minus 1 pairs. So what can be the number of functions is 2 power n minus 1. 2 power n minus 1. Simple thing, simple concept. But if you're not able to understand, no need to worry. Just remember this formula, 2 power n minus 1. Right. One important topic I would like to start. That is multiplexer, but not today. No need to worry. So, so every day in the remaining days, it may be extended. Be ready for that. So, any questions? Now you can raise the hand, sir. Rohit.
Good evening, sir.
Your voice is low or some disturbance is there.
Hello, sir.
Yes, yes.
Hi. Yes, sir. That maximum number of function possible, sir. Functions.
Maximum number of. Simple thing is when we are having
Sir,
two.
here if n means 0 variables, then that equation follows that two functions are if n 0, sir. Then
Is it realistic to say that 0 variable functions?
sir. Then that equations gives that
Listen.
Sir.
Is it existing 0 variable function?
No, sir. But I am confusing with that equation, sir.
So you must be realistic, right?
Yes, sir.
It is not possible with the 0 variables.
Yes, sir.
Which are possible, you can go with 1 variable, 2 variable, and so on. You can proceed.
Okay.
Right? Is that a doubt?
Okay. Yes, sir.
Okay. I think Ajay got selected. Okay. Ajay. Ajay, are you there?
Sir, hello. Hello, sir. Hello. Hello.
Yes, Ajay.
Good evening, sir. Hello.
What happened?
Sir. Hello.
Voice, mic test. Ajay, what is your doubt?
Sir, combination circuit compare. Comparator la equation ఉంటుంది.
What is that?
Comparator la equation, sir.
Comparator equation. It was yesterday's, right?
Yes, sir.
Okay, wait till the end. I'll open that slide, sir. Let me complete if anyone is having doubts here. Otherwise, whatever the doubt you have, you can WhatsApp me. I will help you.
Okay, sir.
Or I will call you if required. You ping me with that. I'll call you because there is another slide, sir. I will help you. Right, Ajay?
Okay, sir.
Ajay, it is audible. Is it audible?
Yes, sir.
Yes. Yeah, I'll call you. You ping me in WhatsApp. I'll call you. If you are not
Okay,
able
sir.
to understand how to write a comparator equation, I'll help you.
Okay, sir.
Right.
Thank you, sir.
Bhavani. Bhavani. Bhavani.
I audible, sir?
Yes, now it is audible. Tell me.
Sir, it's my question is from day 8, sir. It is
Oh.
about K-map.
Okay, K-map. Okay.
Sir, it is classroom practiced question, and the in question itself, it is intentionally given K-map wrong, sir.
My question or in the classroom practice question?
Yes, sir, it is classroom practice question, and the question is, it is in the question, it is intentionally given wrong, sir. It is like 1011.
No, that is I have taken in the class, right?
Yes, sir.
Such a question I've done already, right?
Sir, you have updated, but I did in a different way, sir. Just, sir, can you please just open the slide, sir?
Classroom practice question I haven't done, right?
It is
Yeah.
done, sir. First question, sir. It is first question. Class. Find number of PI, CPI, and redundance. Minimal expression.
What I discussed in the class or classroom practice questions?
You have discussed in the class, sir.
That is
First
not
question.
classroom practice question, please. My question is different. Classroom practice questions are different. Classroom practice questions means whatever the questions which are given in your PDF.
Okay, it is not from PDF, sir.
Okay, then my discussion question, right? So I remember the question, right? Okay, I can write it. Instead of going to those slides, I can write that question, right? Okay. Intentionally, it was given wrong K-map.
Yes, sir. Yes, sir.
Right. I will write A, B, C, 0, 0, 0, 1, 1, 0, 1, 1, at 0, 1. This was a K-map, right?
Yes, sir. Yes, sir.
Then what happened?
Sir, can't we just move the whole column to the right side, like left side,
That's
like
what I'm doing.
1 to the left?
That's what I'm doing, right? That's what we are doing. For that question, answer is right. This is same, but this one should be shifted left. Then I have minimized, right? This one grouping, the second grouping. What is the doubt? That is the correct one. C plus AB is the correct one. For this question, answer is C plus AB. Number of prime implicants is 2. The essential prime implicants also 2. That's what I mentioned. Go through the slides. Go through slides, please.
Okay, sir. Thank you.
If the listen, don't worry. If the question is given correctly, what to do?
No, sir.
Right.
In the classroom, you just swapped the 1 1 to left side and 1 0 to left side. You didn't change the 1 1, sir.
Two questions I
Midterms.
solved. Two questions I solved. Please. Two questions I have solved.
Okay.
By using this one method, and another question, not another method. Another question. If the question is like this, how to solve?
Okay. Okay, sir.
This is different. This is different.
Okay, sir. Thank you.
Right?
I'm sorry. Thank you, sir.
Thank you. Ashish. Sahil.
Good evening, sir.
Very good evening, Sahil.
Sir, my doubt from yesterday's class.
Oh. Please wait. I'll open the slide, sir. What is the question? Can you say?
Sir, in parallel adder, we take del as a delay.
Yes, n delta.
Sir, you told that it is the maximum of T,
Listen,
C and TS.
Listen carefully.
Ji.
The question is like this: a full adder is taking 5 nanoseconds delay. Then what is a 10-bit adder delay? Then what do you do? 10 into 5, right? Right?
No, sir, we are
Listen.
del.
Right. Del is a 1 delay. Other way we can specify a full adder is taking 2 nanoseconds for carry, 5 nanoseconds for sum. Then do we use this formula? Right? Are you there?
Yes, sir.
Sahil, when it is provided with only one, full adder is taking some delay. Only one delay, that is delta. But a full adder is taking, right, carry time separately, sometimes separately specified. Then we go with the triple carry adder, n-1 TC plus maximum of TS comma TC. But here, in this case, it is not provided 2 delays. Then what should I do? N delta.
Okay, sir.
Right?
Got it,
If
sir.
it is provided with 2 delays, we go with triple carry adder.
Thank you, sir.
Right. Just a minute. Right. Some more people are waiting. Okay. Sahil. Okay. Ashish. Ashish.
Good evening, sir.
Very good evening, Ashish.
Sir, my doubt is on 9F, sir.
Okay, 9F. Okay.
Sir, will you please explain the time distribution that you have done
That
here?
you will understand after completion of sequential. The
Sir.
only thing you need to understand is a T n bit is equals to n clock cycle. 1 clock cycle, 1 bit addition is possible. N clock cycle, n bit addition is possible. And the delta, if it is provided full adder delay, the clock period must be more than delta. That's it. Just understand these things. How I am splitting this time, you will understand after getting into sequential.
Sir, the second statement you have told, can you explain it one more time? The second statement.
Now itself, you are saying?
Yes, sir. Now I just
Right. So clock period must be greater than delta. What is delta? Full adder delay.
Okay, sir. So
Because addition should be completed only that much if you are provided, it's a problem, right?
yes, sir.
So for applying inputs, input must be stabilized, then output is stabilized. So before applying next bits, output must be stored, all these. So
Yes,
at
sir,
next
yes.
clock edge occurrence, flip-flops are going to capture the data. That means inputs are exactly at the clock edge occurrence if it is settling, by the time it is capturing previous one. So all this you will understand after getting into sequence, because what is setup time, what is flip-flop delay, what is shift register delay, all this you will understand.
I got it, sir. Got it. Thank you, sir.
Thank you. Any more doubts?
No, sir.
Okay, thank you. Thank you, Ashish. Pranit.
Sir, good evening, sir.
Very good evening, Pranit.
Sir, can you justify this statement, sir? The dual of ith min term is max term. 2 power n minus I minus 1.
That is for what is that? Self-dual function.
How it is? Can you just explain it, sir?
See, ith means, for example, if I take like this, see, ith is a number, right?
Yes, sir.
For example, let me take three variables. It is 2. What is the combination? 0, 1, 0. Then what I
Yes.
said, if this is a minterm, 1, 0, 1 should not be a minterm, right?
Yes, sir. Corresponding minterms.
Right? This should
Yes.
not be a minterm. This must be a max term. That means 5 is a max term, right?
Yes, sir.
So ith, what is the next one? Max term? 2 power n minus I minus 1. Am I right?
Yes, sir.
Then what is it here? 8, because 3 variable. 8 minus 2 minus 1. How much is that? 5th. 5 is max term.
Yes, sir. Yes, got it.
Hmm?
Yes, sir. Thank you, sir.
So where you have studied this?
In bits and bytes, it is given, sir.
Yes, yes. That's what I've been explaining. Instead of
Okay.
making complex here, simply I mentioned that complementary vector.
Okay, sir.
So
Thank
if I give a statement, you are understanding statement, right?
Yes, sir.
But how it is, you are not understanding.
Okay.
That is the reason I explained in another way.
Okay, sir.
Okay.
Thank you, sir.
Thank you. Pradeep Kumar.
Good evening, sir.
Yes, good evening. Tell me.
Sir, my doubt is from Boolean algebra.
Yeah. We are in combination now. You are asking Boolean algebra. Tell me question.
Sir, let two function is given f1 and f2. If OR operation is done, then we get A union B.
Yes.
Then what should we get for NAND operation?
First.
NAND gate operation.
So what we get for NAND?
Yes, sir.
So F1, F2. Can I write like this?
Yes, sir.
Here we are getting F1 intersection F2.
Yes, sir.
What we get here? Complement already we discussed.
Yes, sir.
That's it. That's it. When we know minterms of here, the remaining are minterms of this complement, right?
Yes, sir.
Understood?
Sir, but I got a question.
See, for example, F1 is 2, 3, 7. F2 is 3 and 6. If I say, then I am doing that and. What we get here? Just 3 only. Then what is complement of this? 0, 1, 2. Right, next 4, 5, 6, 7. All these are minterms of this.
Yes,
This is and is resulting sigma m of 3. And complement of that is nothing but remaining all.
yes,
Right?
yes, sir.
This is sigma m of 3. It is pi m of 3. Pi m of 3 means sigma m of remaining numbers.
Yes, sir.
Clear?
So, but in the question itself gives F1 is 0, 1, 3, 5. The
F1 is
6, 0, 1, 3, 5.
F1 is 0, 1,
1,
3,
3,
5.
5.
Okay.
And
F2,
F2 is 6, 7.
6,
7.
7.
Yes, sir.
Then you are expecting NAND.
Yes, sir.
It will be 1. That means sigma m of 0 to all that 7. Can you say why? What is intersection? And
Yes, sir.
0. What is complement of that? It is 1.
Yes, sir.
Right? That means sigma m of 0 to 7. All are minterms. Function is 1 means for each and every combination function is 1. Because intersection is 0. Why? We don't have any common minterms. Then function is 0, not sigma m of 0. Function is 0.
Okay, sir. I got it, sir.
Right. Thank you. Pradeep Kumar Jena. Abhijit.
Good evening, sir.
Very good evening, Abhijit.
Sir, today's first problem we have discussed. Today's first question.
Yes. Yes, I'm going. First. Okay. Yes. What happened?
Sir, here, if for F1, if the
FA1.
sum time is lesser than FA1.
Okay.
If some time,
Then it is
if time
tending
taken
to
for
be-
the
tending,
less
yes,
than.
Yes, I'm understanding. It is tending to become 1. Again, it will be
Yes,
false.
sir.
Finally, what is that here? Stable, whatever was there. Because with 0, 1, 0, it is tending to become 1. Very good. Good question. And when it is becoming 1, again it is becoming 0. That's what it tending to become 1, again back to 0. What is
Yes, sir, then
stable? 0.
What will be the propagation in that case?
So
If some
you are
time
saying
is
that
less than carry.
see, it is very small, you are saying, right?
Yes, sir.
You are saying that it is very small.
It,
Very small means, so before it is getting here, it is again back to that, right?
yes, sir.
For example, here it is 5 nanoseconds. Here it is getting 1, it is 5 plus 5, 10 nanoseconds. By the way, what happens? It is changing, right? For example, this is 5 nanosecond, carry is 5 nanosecond, sum is 2 nanosecond, for example. Here it is getting at 5 nanoseconds. Before that, it is becoming 1. Right?
Yes.
It is becoming 1. See, understand correctly. It is becoming 1. After 5 nanosecond, what happens again?
It will again.
Again
0.
falling to 0. In how much time? In 2
0.
nanoseconds. But here we are getting 1, 5 plus 5, 10 nanoseconds, right?
Yes, sir.
This is again back to 0 in how much time? 5 plus 2. Sorry, 2 plus 2 or 2 plus 5 plus 2. Am I right?
Yes.
At 5 nanoseconds, again starting discharging. So meanwhile, it is becoming 1. So in 5 nanoseconds, again started discharging. 5 plus 2, 7 nanoseconds is again back to 0. But here it is getting 1 in 10 nanoseconds. 5 plus 5 plus.
Yes, sir.
Finally, it is settling to 0. By this time itself, it is settling. You are saying that some time is very small. Not a problem. If carry is taking more time, carry propagation is taking more time, by the time it is going up and again back. Disturbances are there. But again settling back to expected, right?
Yes, sir.
Abhijit.
Then there will be no propagation delay.
We don't need
for
to consider.
S1.
We don't need to consider.
For S1 also.
Everywhere, right? It is tending to become 1, again back to 0. Final, what is
Sir,
that?
if,
0 itself. So whenever such problems are created, that's what I already mentioned. Some glitches will be there. Second example of propagation delay, what I mentioned, because of unwanted signals, unknowingly we are getting at output a glitch. A glitch can be eliminated by making that arrival of inputs is same. That will take care. In any such cases are there, in a design, will take care. If it is creating any disturbance. So, for example, whatever that 8 nanoseconds at the time, if you are saying that it is for at 8 nanoseconds, if you are saying it is 1, functionally wrong, right?
Yes.
At 8 nanoseconds, if you are seeing this here, it is 1, will be problem. Yes or no?
Yes, sir.
In that case, we make arrival of inputs is making this not going to 1. So whenever it is creating a problem, that is in our hand, by adding buffers, we can change. But in this case, for specific conditions, we won't do that. finally, what we say here, how much time it takes to stable. But when such circuits are given, do we wait for this much time only? 8 nanoseconds?
No.
No, because for a specific inputs we are analyzing. But in reality, how much time we wait? 2 plus 2 plus 2, 6 plus 5, 11 nanoseconds we wait. In 11 nanoseconds, it may be going up and again coming back. There won't be such problems, right? Abhijit.
Thank you, sir.
Abhijit.
Yes, sir. Thank you.
For a
Got-
specific input combinations, we are analyzing. But when you are analyzing this circuit in general, or if I use this circuit in a particular processor, then I don't say that it is 8 nanoseconds. What I say? 11 nanoseconds I need to wait. Why? Carry time, and some time. I have to wait for 11 nanoseconds. In that 11 nanoseconds, it may be getting glitches. Yes, getting glitch and coming back again, settling. Abhijit.
Yes, sir. Yes, sir. Got it.
Right. Thank you.
Thank you, sir.
Ravi Teja. Ravi Teja. Ravi Teja, it is not audible. Ravi Teja, it is not audible.
Hello, sir.
Yes, tell me.
Sir, in the by BCD to XS3, sir.
BCD to XS3, right? Okay.
Yes.
Just BCD to XS3, BCD to XS3. Okay.
So next, sir.
Okay. What happened?
Next, sir.
Okay.
Sir, in that, sir, మీరు అందులో
చెప్పు పర్లేదు.
సార్ బీసీడీ డైరెక్ట్ బీసీడీ లోకి కన్వర్ట్ చేశారు సార్ మీరు 0765411.
బీసీడీ కాదు నాన్న, అవి ఇన్పుట్ కాంబినేషన్ నంబర్స్. కేమ్యాప్ లో మనం ఏబిసిడి పొజిషన్స్ రాయాలంటే ఏం రాస్తాము? 0 to 15 రాస్తాము. ఆ 0 to 15 ఏ కాంబినేషన్ నంబర్స్ తో చేస్తాము? ఒకవేళ 011 ఏబిసిడి 011 అన్నాం అనుకో, కేమ్యాప్ లో పొజిషన్ ఏంటి? 1
నో సార్, 7. yes sir.
అందుకని 7 రాస్తాం.
అదే సార్, ఇప్పుడు మనకి కేమ్యాప్ లో
బీసీడీ కన్వర్ట్ చేయడం కాదమ్మా, దాన్ని ఏమంటామంటే ఇన్పుట్ కాంబినేషన్ నెంబర్ రాస్తున్నాం.
ఇన్పుట్ కాంబినేషన్ నెంబర్ రాస్తున్నాం సార్. ఇప్పుడు కేమ్యాప్ మనకి రివర్స్ ఆర్డర్ లో రాస్తే మనకి ఇది రావాలి కదా సార్ మళ్ళీ.
ఏంటి రివర్స్ ఆర్డర్ లో?
అంటే ఇప్పుడు కేమ్యాప్ కి కన్వర్ట్ చేశాక అంటే ఫంక్షన్ రాస్తున్నారు కదా సార్ కేమ్యాప్ ఉపయోగించుకొని.
అవును.
రాసిన తర్వాత మళ్ళీ మనకి ఇది ఉంటది కదా సార్ 84 -2 -1 ఆ కోడ్లకే మళ్ళీ మనకి రావాలి అంటే అట్లా రాదు కదా సార్.
ఏం కన్వర్ట్ చేస్తున్నావు ఒకసారి క్లియర్ గా చెప్పు. టెన్షన్ పడకుండా నిదానం చెప్పు.
సరే ఇప్పుడు
నిదానం చెప్పు, నీవు ఏం కన్వర్ట్ చేస్తున్నావు?
అదే సార్, ఇప్పుడు మనకి BCD టు
ఒకవేళ నేను 011 ఇస్తే అవుట్పుట్ లో PQRS కనుక సబ్స్టిట్యూట్ చేస్తే కనుక నాకు 0100 రావాలి. వస్తుందా లేదా చూడంతే. మనం చేస్తున్న కన్వర్షన్ ఏంటి? 84 -2 -1 BCD ఇన్పుట్ కనుక ఇస్తే ఈక్వలెంట్ XS3 రావాలి మనకి, అంతే. ఇదన్నీ మళ్ళీ దీని ఎందుకు రివర్స్ చేస్తున్నావు?
అదే సార్, మీరు కేమ్యాప్ రిప్రజెంటేషన్ చేస్తున్నారు కదా సార్.
కేమ్యాప్ రిప్రజెంటేషన్ చేస్తున్నప్పుడు ఇందులో ఎక్స్ప్రెషన్ వస్తుందా? ఈ ఎక్స్ప్రెషన్ లో నేను ఒకవేళ ఏబిసిడితో రాస్తున్న ఎక్స్ప్రెషన్, అవునా?
అవును సార్.
ఆ వచ్చిన తర్వాత ఏబిసిడి ఒక కాంబినేషన్ సబ్స్టిట్యూట్ చేశారు అనుకో పిలో అండ్ క్యూఆర్ఎస్, PQRS ఈ 4 అబ్జర్వ్ చేస్తే ఒకవేళ ఏబిసిడి 011 ని ఈ 4 ఎక్స్ప్రెషన్ సబ్స్టిట్యూట్ చేస్తే PQRS ఏం రావాలి? 0100 రావాలి, అంతే.
అవును,
మనకు రావాల్సినది. నువ్వు దీన్ని ఎందుకు కంపేర్ చేస్తున్నావు మళ్ళీ? ఒకవేళ ఏబిసిడి 0111 సబ్స్టిట్యూట్ చేస్తే కనుక ఈ PQRS ఎక్స్ప్రెషన్స్ ఉంటాయి, ఏబిసిడిలో ఎక్స్ప్రెషన్స్ వస్తాయి, అవునా?
అవును సార్.
ఈ ఏబిసిడి ఎక్స్ప్రెషన్ లో సో పిక్యూఆర్ఎస్ ఎక్స్ప్రెషన్స్ లో ఏబిసిడి కాంబినేషన్ 0111 సబ్స్టిట్యూట్ చేస్తే పిక్యూఆర్ఎస్ రిజల్ట్ ఏం రావాలి అంటే 0100 రావాలి. అంతే మనకు కావాల్సింది.
మరి కే మ్యాప్ రిప్రజెంటేషన్ సార్?
కే మ్యాప్ రిప్రజెంటేషన్ కొరకు ఈ నెంబర్స్ ఇచ్చాను మనం. కే మ్యాప్ లో ఎందుకు సబ్స్టిట్యూట్ ఎందుకు చేస్తున్నావు?
అది మీరు చెప్పారు కదా సార్ చేయమని.
కే మ్యాప్ లో సబ్స్టిట్యూట్ చేయకు. నేను చేసేది ఏంటంటే ఈ కాంబినేషన్ 0111 ఈ కాంబినేషన్ ఎక్కడ నేను ఒకవేళ 0111 కి మింటాం అనుకో కే మ్యాప్ రాస్తాను. సరిగ్గా చూడు, నీకు అర్థమవుతుంది. ఏబిసిడి 00011110 00011110 ఒకవేళ ఏబిసిడి 0111 కనుక మింటం అయింది అనుకో, మింటం ఎక్కడ రాయాలి? ఇక్కడ రాయాలా?
అక్కడే సార్.
కానీ మనం ఇచ్చిన నెంబర్ 0111 కి నెంబర్ ఎంత ఇచ్చాము? 1 ఇచ్చాము.
1 ఇచ్చాము సార్.
ఈ 1 దగ్గర కనుక నువ్వు మింటం రాసావు అనుకో ఫంక్షనాలిటీ తప్పైపోతుంది. ఎందుకంటే కే మ్యాప్ యూజ్ చేస్తున్నప్పుడు ఈ ఏబిసిడి 0111 అనేది ఇక్కడ ఉంది కదా, అక్కడ మాత్రం మింటం పెట్టాలి. అంటే ఇది మింటం 7 లేకపోతే 1?
మింటం 7 సార్. అది
మింటం 7. అందుకని మింటం సపరేట్ గా రాశారు, కాంబినేషన్ నెంబర్ సపరేట్ గా రాశారు. ఒకవేళ ఇలా ప్రొసీడ్ అవ్వాలి అంటే ఈ 1 తీసుకొని నేను ప్రొసీడ్ అవుతే రాంగ్ వస్తుంది. ఎందుకంటే ఒకవేళ 7 కనుక ఇప్పుడు క్యూలో ఉంది, క్యూలో ఏంటి ఇక్కడ మింటం, ఇది మింటం కదా.
అవును సార్.
అంటే ఈ మింటం ఎక్కడ రాస్తాను? ఇక్కడ రాస్తాను 1 లో కాదు. ఏబిసిడి 0111 అంటే ఇక్కడ రాయాల్సింది మింటం. ఒకవేళ క్యూ ఎక్స్ప్రెషన్ రాస్తున్నప్పుడు ఇక్కడ మింటం 1 అయింది అంటే ఈ మింటం 1 ని ఏ పొజిషన్ రాయాలి కే మ్యాప్ లో? ఇక్కడ రాశారు అనుకో తప్పు అవుతుంది, ఇక్కడ రాయాలి. అర్థమవుతుందా?
ఓకే సార్. అందుకని
ఇన్పుట్ కాంబినేషన్ నెంబర్స్ ఫైండ్ అవుట్ చేస్తున్నా ఏబిసిడి ఆర్డర్ లో విత్ 8421 వెయిట్స్. అర్థమవుతుందా? ఇది ఒక బిసిడిఏ. 84 -2 -1 అనేది ఒక టైప్ ఆఫ్ బిసిడి. XS3 అనేది అనదర్ టైప్ ఆఫ్ బిసిడి. సో ఇవన్నీ డిఫరెంట్ బిసిడిస్. కానీ ఇది ఈక్వల్ అవ్వాలి అంటే ఒక లాజిక్ సర్క్యూట్ కనుక డిజైన్ చేస్తే ఒక టైప్ ఆఫ్ బిసిడి ఇస్తే అనదర్ టైప్ ఆఫ్ బిసిడి రావాలి మనకి. అది కావాలి. అందుకని కన్ఫ్యూజ్ అవ్వకు, కంగారు పడకు. రైట్ రైట్.
in the last page sir, 25th I think.
25th ఓకే. ఏమైంది?
24th.
24 ఓకే.
not this sir.
ఏమైంది?
లాస్ట్ పేజ్ సార్.
ఇదే కదా లాస్ట్ పేజ్.
అదేనా సార్? అదే మీరు మింటమ్స్ చెప్పారు కదా సార్, అది ఎసెన్షియల్.
ఈ ఎసెన్షియల్ చెప్పిందా? ఇక్కడ ఏమైంది?
ఫస్ట్ టేబుల్లో టేబుల్స్ అన్నిటిలో మనకి ప్రైమ్ ఇంప్లికెంట్స్ 4 వస్తాయి. అది ఫస్ట్ టేబుల్ సార్.
ఇందులో 4,
ఎసెన్షియల్ ప్రైమ్ ఇంప్లికెంట్స్
కూడా 4.
ఎసెన్షియల్ కూడా ప్రైమ్ 4 సార్.
ఎందుకంటే ఈ గ్రూపింగ్ లో ఒక క్యూబ్ ఉంది, అది దాంట్లోనే కవర్ అయింది. అంతే కదా మనకు కావాల్సింది.
అవును సార్.
రైట్. దీంట్లో 8 ఉన్నాయి కదా.
అవును సార్. ఇంతకుముందు మీరు అది చెప్పారు కదా సార్, అది కే మ్యాప్ అనేది రాంగ్ ఇచ్చారు అన్నది, ఆ ప్రాబ్లం ఒకసారి చూపించండి సార్.
ఆ ప్రాబ్లం ఎవరు అడిగితే చేశాను కదా ఇందాక.
అవును
చేసినాము చూస్తాను. ఇక్కడ ఏమైంది
సార్? ఇందులో ప్రైమ్ ఇంప్లికెంట్స్ మీరు 2 అన్నారు కదా సార్. ఇందులో
2
అది ఎట్లా సార్?
ఎన్ని గ్రూపింగ్స్ ఉన్నాయి మనకి?
2 గ్రూపింగ్స్ ఉన్నాయి.
2 గ్రూపింగ్స్ కదా.
ఓకే. ఆ ఇంప్లికెంట్స్ తో మనకి రిలేషన్ లేదా సార్?
ఎన్ని ఉన్నాయనేది కౌంట్ లేదు.
ఓకే.
ఈ గ్రూపింగ్ ఒకటి ప్రైమ్ ఇంప్లికెంట్. ప్రైమ్ ఇంప్లికెంట్ 2 ఉన్నప్పుడు ఎసెన్షియల్ 4 ఎట్ అవుతాయి.
ఓకే సార్.
ఒక ప్రైమ్ ఇంప్లికెంట్ ని ఎసెన్షియల్ కాదు చెప్తాం.
అవును.
ప్రైమ్ ఇంప్లికెంట్ మనకు 2 కదా, అందుకంటే ఎక్కువ ఉన్నాయా?
లేవు సార్.
ఈ రెండింట్లో స్పెషల్ క్యూబ్స్ ఉన్నాయి కాబట్టి 2 ఎసెన్షియల్ అంటున్నాం.
ఓకే సార్.
ఓకేనా?
ఓకే సార్. థ్యాంక్ యూ సార్.
ఓకే. వీరబాబు వీరబాబు
హలో.
ఎస్ వీరబాబు.
సార్ మీరు ఇమేజ్ కనబడట్లేదు సార్ నాతో.
ఏం చేయండి నా చేతిలో అయితే ఏమీ లేదు.
సార్ నేను ఏస్కి ఫోన్ చేశాను సార్ అక్కడ. ఫోన్ చేస్తే వాళ్ళు టెక్నికల్ డిపార్ట్మెంట్ వాళ్ళు ఉండి మీ ఫోన్ లోనే ప్రాబ్లం ఉంది అన్నారు. మళ్ళీ జూమ్ యాప్ అన్ఇన్స్టాల్ చేసి ఇన్స్టాల్ చేశాను సార్. 2 days అయింది సార్, రావడం లేదు అసలుకి.
దానికైతే మరి నేనేం చేయలేను. ఒకసారి చూడు, వేరే డివైస్ లో లాగిన్ అయ్యి చూడు. ఒకవేళ ఫ్రెండ్ దాంట్లో ఒకవేళ ఒక 10 minutes అలా చేసి చూడు.
ఓకే సార్.
ఇంకా ప్రాబ్లమ్ కరెక్ట్ గా రెక్టిఫై అవ్వాలంటే వేరే దాంట్లో లాగిన్ అయితే చూస్తే అక్కడ కూడా ప్రాబ్లం వచ్చింది అనుకో
సార్, చూడు
ప్రాబ్లం వస్తుందా లేదా. ఒకవేళ అక్కడ లాగిన్ అయితే ఇప్పుడు మిగతా వాళ్ళందరికీ వస్తుంది.
అవును సార్, నాకు కూడా వచ్చింది సార్.
200 members కి ఆల్మోస్ట్ వస్తుంది. ఒకరిద్దరికి కొందరికి రావట్లేదు అంటే అది ఆల్మోస్ట్ ఇష్యూ విత్ యూ ఇట్స్ రైట్. ఇప్పుడు నేననేది ఏంటంటే ఒకవేళ ప్రాబ్లం ఉందా లేదా తెలుసుకోవాలంటే వేరే సిస్టమ్ లో లాగిన్ అయ్యి చూడండి.
ఓకే సార్, అలాగే సార్. థ్యాంక్ యూ సార్. థ్యాంక్ యూ సార్.
మనీషా. Manisha.
Hello. Good evening, sir.
Yes. Good evening, Manisha. Tell me.
Sir, in adders, I have a doubt, sir. You solve some questions now, sir. In that last question, I have a doubt.
This one?
No, sir. The next one.
Okay.
No, sir. This one only.
This one only? Okay.
Yes, sir. Sir, here you mentioned that 8 nanoseconds now, sir. Sir, sir, not this, sir.
Why? What is the problem?
Sir,
the only
you
thing is,
A3, A2, A1 and A0 to be 1, 0, 0, 0 and B3, B2, B1, B0 to be 1, 1, 1, 1, sir. And C0 is 1.
I have used that A3, A2, A1, A0 is 1101, B3, B2, B1, B0 is 1111, C0 is 0.
Sir, that's the first question, sir. And you said another 2 questions, sir. Like you gave some examples and you said that have to find.
This one?
No, sir, the next one.
Next one I have given as homework, right?
Yes, sir. In that, like I have a doubt, is it 8 nanoseconds or no, sir, is it 10 nanoseconds? Like that I have a doubt.
Answer you're asking me?
Connection is not good, so I just noted that some and did that, sir.
Okay.
Like I just logged.
You are asking me answer? You want me to say answer?
Yes, sir.
Then it is 10 nanoseconds.
Yes, sir. Thank you. Sir, I have another doubt. Like in look ahead subtractor is there, no, sir? In that, there is like you gave one conclusion by giving some expression, no, sir? In look ahead subtractor, sir.
Add and subtract, right?
Yes, sir. Carry look ahead adder. Sorry, sir. Carry look ahead adder.
CLA.
Yes, sir.
In CLA, what I concluded?
Sir, you gave one expression for carry, no, sir?
Yeah, yeah.
Have
here,
to...
here. Look at this.
Yes, sir. Here, so, is there any generalized expression, sir?
It becomes very complex. No need to remember.
Sir, on this, yes, sir.
I can give for n bits. I can give for n bits. Like Pn minus 1, Pn minus 2, Pn minus 3, so and so, C naught, and so and so. I can give you that, but not required.
Sir, but on this concept, there will be any question like it's much lengthy, no, sir. Then how can we solve this one in an exam time like that?
They won't give you such questions because to calculate delay itself it takes more time, right? Even
sir,
though they are...
Okay, sir. Sir, and all these questions are somewhat like by knowing this concept, I feel like it's okay, but after when we start doing something, we feel like some sort of difficulties we just face, sir. So that I need for every question, I need some questions to solve.
Yeah, initially it takes time. Initially it takes time. Once you are getting clarity in the concept, when you are solving next questions or next time, obviously it will be easy. May not be same question. You may be going to another question. Then you feel confident.
Yes, sir.
Right? So first time, obviously it will be like you will be having a doubt whether I am doing correctly or not.
Yes, sir.
Obviously,
Sir, not like, sir, like you are saying class for 4 hours now, sir. In that, like I may not get all the types of problems which you are covering.
everyone will not get. Some
Yes.
people may be answering immediately, and I should not say these words better. Some people have been taking multiple times coaching.
Yes, sir.
No need to worry about that. Others are getting, I am not getting.
Yes, sir.
Don't need to worry about that. So, but whether you are working or not, yes, you are working, then obviously there will be results.
Yes, sir.
Feel confident. Don't lose your confidence. Right? So, any more doubts?
Another, sir. In 25th frame, sir.
25th frame.
No, sir. Previous one.
Okay.
Here you mentioned like for n number of like different types of combination. You said some.
So first, last. All zeros to all ones, right?
Yes, sir.
When I'm saying that 3 bits, 0, 0, 0, last one is what? 1, 1, 1. How to get that 0, comma, 2 power 3 minus 1. 2 power 3 is 8, 8 minus 1 is 7.
Yes.
That's why I've written. 1,
yes, sir.
1 comma 6. How do we get that minus 1 instead of minus 1 and minus 2? And so and so. Last one may be difficult to catch you immediately. Right? 2 power n minus 1 minus 1. Half just before half.
Yes.
2 power n is what? Last one. Half is what? 2 power n minus 1. Because 2 power n by 2.
Yes, sir.
2 power n by 2. Half. 2 power n minus 1. That is 1 and just before that. Because we are starting with 0.
Yes,
That
sir.
one and just before that one. Just fold all the combinations.
Yes, sir.
Writing on a page, just fold it.
Yes.
That's what we get.
Sir, the next like the next step.
Yeah, next step.
In that next step, I have a doubt, sir. Like you mentioned.
This one you are saying?
Yes, sir. How it came, I didn't understand.
Actually, if 0 is there, 7 should not be there. If 7 is there, 0 should not be there. From these two, 1 can be as a min term.
Yes, sir.
For self-deal. If 1 is there, 6 should not be there. If 6 is there, 1 should not be there. From these two, 1 should be there. 1 min term. Which one is that? Doesn't matter. So from these two, 1. From these two, 1. That means I'm choosing 1 from each pair.
Yes, sir.
That is the reason. From 2, 1, we are choosing 2C1 ways. From 2, I'm choosing 1, 2C1 ways. From 2, I'm choosing 1, 2C1 ways. From 2, I'm choosing 1, 2C1 ways. That's it.
Sir, but here 2 into 2 into so on up to whole 2 power n minus 1. How did you wrote, sir, that one? I didn't understood.
Actually, when we have 2 power n combinations, how many pairs will be there?
2 power n combination.
So when we have 2 power n combinations,
yes, sir.
How many pairs will be there? By 2, right?
By 2, okay.
Then what is the 2 power n minus 1, right?
Yes, sir.
2 power n minus 1 pairs are there?
Yes, sir.
That's what I will do. 2 power n minus 1, because number of pairs. If you are having 4 pairs, 2 power 4. When you are having 2 power n minus 1 pairs, what I write? 2 power number of pairs.
Okay.
Understood?
Yes, sir.
No need to think that much about this logic for objective exams. Just I've given a concept.
Yes, sir.
If required, I'll explain once again when I find time. Right? So no need to worry about this. Just understand this, what we need to do, how to get the answer. If possible, try to remember.
Yes.
Right? Any question?
Sir, no, sir. Thank you.
Then thank you. Right. तो है जाक्षु तो है जाक्षु Are you there? I have enabled you to talk. I'm not getting any voice. So is Akshudu. I'm not getting any voice. Please type in the chat box if you need any help from any of the questions or frame. Yeah, people were asking about screenshots. I didn't know that. I didn't check. Someone is asking for screenshots. Let them take. Anyway, we are going to upload the slides. So, Akshudu, can you type any question? I'm not able to hear you. You have Chakravarti. Already I have discussed that question, right? Go through the slides, sir. You will get an answer. Chakravarti. And Toyaj Akshudu, your answer is correct. Propagation delay, I haven't talked in carry look added. Simply I mentioned that as a number of levels have been increasing, in this number of levels have been increasing, see what happens here? Propagation delay is increasing. When propagation delay is increasing, no point in designing separate circuit, right? When number of levels is increasing for number of bits is increasing, then what is happening? Propagation delay of this additional circuitry is increasing. So by using additional circuitry, we want to save time. But finally, what is happening? Unnecessarily propagation delay may be exceeding. So is that true? Oh, propagation. How you are getting propagation? Okay. See, 0, 1, whatever is there on input carry will be output carry. For 1, 0 also, whatever is there on input carry will be there on output carry. So for AB 0, 1 and 1, 0, input carry is propagated to output carry. When AB 0, 1 or 1, 0, propagation is occurring. That we are checking with XOR only, right? When AB 0, 1 or 1, 0 means when A and B are unequal. That is XOR function only, right? So when AB 0, 1 or 1, 0 in these two conditions, it is propagating. It is propagating. It is propagating. So propagation is occurring when AB 0, 1 or 1, 0. Right. Any more doubts? You can raise the hand, sir, if you have doubts, sir, if anyone is there. Right. Ashutosha. So if you are using weights, for representing BCD. See, in this, first one is what? 8421 BCD. 8421 or weights are used for representing decimal digits. Coming to XS3. What is coming to XS3? Natural BCD plus 3. That means, are we using weights for this position, sir? No, rules is different. It is not weighted BCD. XS3 is non-weighted. XS3 is non-weighted. Coming to 8421 BCD, weighted BCD. And coming to this 84 minus 2 minus 1 BCD means again weighted BCD. Again weighted BCD. Ashtosh. So weighted means if you are using weights for representing decimal digits, then it is weighted BCD. But in XS3, am I using weights for representing? No. The positions are not represented with weights. Then it is non-weighted BCD. It is non-weighted BCD. Ashtosh. Right. Coming to complementary or self-complementary or not. For each and every representation, if complement is existing in the set, then it is self-complementary. So XS3, if you are observing 0011, complement is there. 0100, complement 1011. 0101, complement is 1010. 0110, complement is 1001. So 0111, complement is 10. So for each and every vector, complement is there in use set. Coming to natural BCD, 0000, complement is what? 1111. Is it used combination? No. So it is not a self-complementary. So for each and every vector used, if complement is existing in use set, then it is a self-complementary. Otherwise, it is not a self-complementary. Ashtosh, I've been explaining that only. Right? Okay. Thank you for understanding. See you tomorrow.